Okay. Good morning, everyone. Firstly, how many of us were at the Web3 Lagos conference or maybe the Accra conference? Okay. Okay. So if people have like maybe if people keep quiet when I ask the questions, I think people will know like the answer to some of the questions, right? So um, we'll be talking about the subject protocol. That is the general idea of this slide. Well, we'll take kind of like an approach that introduces some concepts that we'll be needing along the way. Okay, so this is John Doe, right? He has a basket of apples. He wants to be sure that all the apples there are green. Like all the apples in this basket, he wants to be sure that they are green. Why? Maybe because if he takes a basket of apple, that there's even one red apple to the market, and the authorities find that out, they can arrest him, right? So how can he achieve this as somebody that was not at any of the conferences?
You can sort them.
Can sort them. How?
Picking and making sure it's
Like okay, like counting them, right? So you pick the first one, you check if it's green, you put it aside. You pick the second one until you have picked all the apples, right? Good. So, but these are the things we are concerned with: the amount of work that we're going to do, and our ability to detect a bad apple. So if we go by what you said, that means if we have 10 apples, we are going to be doing like, um, let's say 10,
checks.
let's say 10 checks, right? If we have a million apple, we'll be doing a million checks, right? Like a million checks means more time. We're spending more time on doing that. So in this case, we have like this might be 15. I think. So we have like 15 apples. So how many checks are going to be done in this case? Like if we are checking each of them, checking each apple in the sequence. As we go from the first, we check it. If it's a green or a red apple, we keep it aside. We go to the next. So if we take this sequence, how many checks are we going to do in total? 14. Okay. I think there's like a problem with this slide, maybe because of what I'm using to view it. Okay, so they're actually meant to be 15 apples, right? So we're going to be having like 15 checks because we're checking each of these apples, each of the 15 apples. So what is the probability of us detecting that a red apple is in this sequence? If we're checking all the apples, that means that if there is a red apple in this sequence, at one point in our 15 checks, we are going to see it, right? And that means that we have 100% certainty of detecting a red apple or a bad apple. Right? That is because like at a point in the process of us doing the checks, we are going to pick that red apple. So that's why we have that 100% certainty. Does that make sense?
Yeah.
Okay. So now this is like another basket of apples. We've checked the first basket, and we did 15 checks, and all of them were like green, so we're good to go, right? All of them were green, but we still did 15 checks, which is a lot of work. But then we were 100% certain. So now we have this other basket, and we want to check like the same thing. Yeah, thank you. So in this case, what is going to be the total work done in this case? Like, how many checks do we need to do to detect a red apple? Okay, it's actually still 15, but in this case, since it's a sequence, right? After the first, we pick the first, it's a green apple, we say okay. We pick the second, it's a green apple, we say okay. When we pick the third and we see it's a red apple, we can stop checking the others, right? And just condemn the whole basket, right? So let's say the total work done is still, like, if we are still going to check all the apples, we are still going to need to do like that 15 checks, right? And also, like, what is the probability of detecting that there's a red apple here? Still 100%, right? Because we're actually checking all the apples. So 100%, good. So the characteristics of this protocol now is that it does, like, we do more work, right? So there were just 15 apples, we did 15 checks. If there were a million apples, like I said earlier, we are going to do a million checks, which is going to take more time, right? But then, even if it's going to take more time to check like a bigger basket, we are going to be 100% certain that there is no red apple in the basket, or that there is a red apple in the basket, right? So after doing all our checks, we can comfortably take our baskets to the market without the fear of being arrested, right? So the question now is, like, can we reduce the amount of work done? Like, is it possible for us to reduce the amount of work done? That is, reduce the number of checks we need to do, right? But still, say, probably have that 100% certainty that there is no red apple in the basket. It's a question, like, if you have an answer, you can.
You have a reduced check to reduce the probability of success.
Yeah, if we reduce the number of checks we are going to do, that means we cannot be 100% certain again, right? Because why we are 100% certain is because we are actually checking all the apples. That's what gives us that 100% certainty. But now we're trying to reduce the amount of checks. We're trying to reduce the amount of work. So is it possible for us to reduce the amount of work but still have 100% certainty? Okay. Yeah. But if we pick a random, say we pick the first 5, that means we are not going to have 100% certainty again, right? Good and fine, we are going to reduce the amount of work done, right? But we are not going to have 100% certainty. Does that make sense? Okay. So basically that's it. So rather than checking all apples, maybe we can check some apples, right? So now we need to now see how this affects the probability of detecting a bad apple. Like, reducing the amount of work done, how does it affect the probability of picking a bad apple? Like, is everybody with me up to this point? Okay. Okay, so what if we just check one apple out of this that'd be 14 in this case. So out of this 14, we just check one apple. What would be the total work done?
One.
One, right? Because we are checking just one apple. Good. But then, what will be the chances of detecting a bad apple?
50.
Huh?
1 over 14.
Would that be 1 over 14? We have basically to know that percent, like that probability, we need to check the number of red apples in the basket and also the number of green apples in the basket, right? So in this case, we have like 7 red apples and 7 green apples, right? So the total number of apples in the basket is 14. We have 7 red apples. So if we pick a green apple, the probability of us picking a green apple is like 7 over the total number of apples in the basket, right? Which is a 50% chance. Also, the probability of us picking a red apple is also 50%, right? Because we have 7 red apples. So 7 divided by the total number of apples, which is 14, would give us 7 divided by 14, that is like 1 over 2 times 100, which is 50.
Are we not making this calculation based on the fact that we can see the colors? What if we can't see the colors?
Yeah, we are making the calculation based on the fact that we can see the colors. So we are going to get to that point, and answer the question. I know where you're going at. Okay. So basically, we've seen that in this case we had like a 50% chance, right? So if we actually do this, like we have a basket, we just pick one apple at random, and based on the color of that apple, take our basket to the market. If we say exactly this combination, we are putting our life at risk, right? We have a 50% chance of going to prison, right? But 50%, that's too much, right? That's too much of a chance to gamble. Okay, how about in this case? In this case, what will be the total work done?
Still one.
Still one, right? Because we're checking just one apple. Yeah. And what is the probability of us like picking a red apple? 1 over 14, right? Which is very, very low. One check, couldn't find. A 7% chance of detecting a bad apple. So basically in this case, if we take this basket to the market, we actually have a 93% chance of going to prison. No, a 93% chance of going to prison. We have a 7% chance of detecting a bad apple, right? Which is like, detecting a bad apple is what keeps us out of prison. Because if we detect a bad apple, we discard the whole basket, right? So if we have a bad apple, we discard the whole basket. But if we are not able to detect the bad apple and we take the basket to the market, then if it's checked, we are going to go to prison. I don't know if it makes sense. It's a 93% chance of us going to prison. Because when we get to the market, the police in the market is going to check all of them, right? And with 100% certainty, the police is going to see the red apple. because the police is checking everything. Right.
So we have it's a 7% chance of going to prison because if he checks, we're going to need green. Then he does the 15 chance. If he does only one check, there's a chance that he will most likely.
If who does only one check?
The policeman.
No, the policeman.
Not
Oh yes, they are not. It's we're trying to reduce our work, not the work of the policeman. The policeman will do his work, right? Yeah, it's the policeman. He will do his work, right? So does it make sense? Why? Okay.
So you said it's a 19% chance of not failing here.
Yes.
Because I remember the last night we had 50-50 and then it was a 60% chance.
Yeah, it was a 50% chance of going to prison, and also like a 50% chance of not going to prison.
Okay, so even if we had a 50% chance, when we had more red apples there, then if the red apples are fewer, then it should reduce the chances.
Like, how do I?
I think it's like probability that is success and failure.
Yes.
So our success, then one minus the success, that's failure.
Yes.
Failure is also going to prison.
Yes.
I think that's your idea.
Yeah.
We have 7%.
So, like, based on that, does it make sense why it's a 93% chance? Like, we're trying to avoid prison, right? So, if we're able to detect a bad apple with 100% certainty, that means our success rate is 1, right? But if we are not able to detect a bad apple with 100% certainty, then okay, let's just think about it this way, right? If I have a 7% chance of going to prison, what does that mean? It means that if, try to look for a good example, like out of 100 times I'm supposed to go to prison, I go only 7 times, which is a good thing for me, right? But that's not the case here. I don't know if it makes sense.
So, what you're trying to do in essence is the actual task is to detect bad apple. So, if you're able to
You're trying to detect bad apples in order to save yourself.
save yourself, that's
Yes.
the actual work you're meant
Yes.
to do. So, you detecting a bad apple is a success
For you.
for you.
Yes.
So that means if you're able to get one bad apple, which is a success, that's 7%, and based on what he said in probability, you let's say do 100 minus the 7%. So what's remaining is failure rate.
Yeah, it's a failure rate.
Yeah.
So your success rate is like the ability to detect the bad apple, which is 7%, which is your success rate. So you have a 7% chance of not going to prison, because that's what you're trying to avoid. You're trying to avoid going to prison, right? And in this case, if you're able to detect a bad apple, you have a 7% chance of not going to prison, which basically means that you have a 93% chance of going to prison. I don't know if it makes sense.
So that means when it is much more easier for you to find a bad apple, you have lesser chance of going to prison.
You have lesser chance of
When
going
it
to
is much
prison.
more harder for you to find a bad apple, you have more chance of going to prison.
Exactly.
So, if you say with one bad apple, we have a 3% chance of going to prison. What if it is in reverse and we have 13 bad apples and 13 red apples and 1 green apple? Are you now going to say we have 7% chance of going to prison?
Yes.
In that
We have
sense.
more
Well,
chance.
yes. Well, we're going to see. Okay.
A little bit to so now that like 14 good and 1 bad, every time we like pick a green one, even though there's a budget, it's counting against us.
Yeah, it's counting against us.
That makes sense.
Because when we pick a green one, we are like, okay, oh, everything is green, right? And we pick another green one, we say, oh, definitely, everything is green, right? And we pick another green one, we say, everything must be green, right? So, for every green apple we are picking, we are affirming our chance of not going to prison, right? But then, when we now, like, we might have convinced ourselves up to, let's say, 97% with every green, okay, 93, with every green apple that we are picking. But once we pick this red apple, it's as if we just send all our confidence, like, down the drain, right? Because just this one red apple we've picked, like, has dashed everything out. Like, all those times of picking green apple, just this one red apple we've picked means that the entire basket cannot go to the market. I also hope I'm not, like, making it more complicated. But let's go to the next one and see, like, an example where we have more red apples. Then maybe we'll be able to, like, see them. Okay. So, I think that's it. Well, okay, the characteristics of this one check protocol now is that we do a constant amount of work, right? Which is like just one check, right? But then our level of confidence is not, like, static. We may have a higher level of confidence or a lower level or a lower level of confidence depending on the amount of bad apples in the basket, right? So if we have more green apples, then we have a lower probability of detecting a bad apple, which is a bad thing for us, right? But if we have more red apples, then we have a higher probability of detecting a bad apple, which is a good thing for us. Does it make sense up to this point?
So the more you take the bad apples, the faster you take the bad apples, the more your confidence will be.
Yes. The faster you detect the bad apples, or, like, the more you detect the bad apples, the more your confidence level. Because once you detect a bad apple, you just scrap the entire basket, right? So you're 100% certain you'll not go to prison because you scrapped the entire basket. It seems a lot of probabilities coming in. I also hope it doesn't, like, confuse us. Well, so far, does everything make sense? Okay, so good and fine, like, we're able to reduce the amount of work done. Going from 15 checks to 1 check, that's 15x reduction, right, for the traders. But that came with a high probability of making a mistake, right? Because when you have all greens and 1 red, if you pick just 1 apple, you feel that, and the apple is green, you feel that all the apples are green, and which is wrong, and that's like a high probability of making a mistake. So can we do better? Is it possible for us to do just 1 check but still have 100% certainty that all the apples in the basket are green? Is it possible? Can anybody, like, just...
Like one check.
Yeah, you do just 1 check,
Yes, I'm
but you do just one check, but you're 100% certain that all the apples are green by doing just one check.
And the apples they are arranged in groups first.
If you arrange it in groups, you're still going to do like one check for each group, right?
Is it possible to separate, like, split them into two and check for
I think that's similar to what he said. Like you're randomly splitting them into two, right? And then you're doing one check from each group. That's like two checks, right? So that's still like more work than one check.
Is it like one check or check once?
You're checking, you're splitting into two, and you're doing one check for each of the let's say groups. In your case, if I'm not like getting the question wrong. So okay. Okay. Ask, like, if you have a question. Okay. So, like, in the course of this discussion, if you have a question, no matter how dumb it sounds, please ask, so you don't get confused.
Is it possible for us to confirm before you put the basket?
Like, confirm before putting it in the basket.
Yes, or you put the basket.
No. Let's say you're not the farmer, right? A farmer brings it to you. So it's your job now to take it to the market and sell. But you need to verify before you take it. Because if they come to arrest, it's you they will arrest, not the farmer.
What if you pass in 2 seconds?
That's interesting. You're delegating work. That's another concept to respect to ZK, right? They call it like that should be more multiple provers. Say like a multiple prover network, but that's like something else.
Is it possible to ask the farmer? Are you sure this is?
Who will say yes?
I will record what he says now.
To see everything at a glance. No, it's not.
Just in a single bracket,
You have to just dip your hand inside. Yeah, you just have to dip your hand inside and trust God.
You can check by feeling.
Hopefully, like maybe a red apple feels different than a green apple. Maybe.
So, all right, the clustering
Algorithm.
clustering, all these things.
You're bringing a computer to the market now. You're bringing a computer to the market now, like you need AI to like for image detection, right? That's way far. Like, sorry, which of them?
Like, the idea right now is to find a faster way of verifying the bad apples and the one that are not bad.
Yes.
In what sense? Like, in normal market sense, or we are still going to it, stuff. Are you asking outside of the ZK stuff?
Yeah, I'm asking in the normal market sense.
In normal market sense, it's very important.
Yes. You have to pick just one.
Okay. The bad ones from the. Say you know go check out for a tree as a
Okay. But you're not the farmer. Okay, but let's see what can be done actually. So this is where the concept of error amplification comes in. Error amplification is a very important concept with respect to ZK. Right. And not just decay, it has its application in other fields too. So imagine we have a function. Maybe we eventually bring a computer to the market. But okay, just imagine we have a function that takes a sequence of apples and gives us another sequence that is 1000 times bigger. So if we feed in 15 apples, we get back 15,000 apples. Right? Okay. But now, like, that function, in order to give us back those 15,000 apples, there are certain things that need to be satisfied. Right? So if we have all apples in the small sequence as green, then all apples in the bigger sequence will be green.
So it's basically just cloning. Like, it takes that and then
Yeah.
it makes clones of
That, it just duplicates it.
okay.
Yeah. So we have a sequence that is green. It checks all of them. If all of them are green, it clones it like 1,000 times. Right.
So it explodes it.
Yeah, it blows it up. So something like this. Say we have a sequence of just 2 apples. 2 of them are green. So it just like clones it and like duplicates it. All the other apples will be green. But if we have an apple in the small sequence that is red, even one, the apples in the bigger sequence will also be red. Okay, so this is we have like 2 apples, 1 green, 1 red. Right? Well, we pass it through that function. The function checks the first one is green, good. It checks the second one is red. So for the fact that the second apple is red, when it blows it up, every other thing is red.
I'm confused.
So but what basically
So
is red
basically,
and the second is red. That means that it's going to give like a lesser red apple and
No,
more
no.
an exploded
In as much as it sees 1 red apple,
okay.
yes, every other apple is adding will be red.
So isn't that the same thing as
That is the function, right?
Huh? No, that's not checking one.
So it means
The function is still doing the 15 checks now. or
Yeah,
it's
the
no
function
matter.
is doing the 15 checks.
So it amplifies the error than detect.
Yes.
So have we then reduced the work done on our own?
It's a
part?
function that is doing it, it's not us.
So that
Right.
means in the general sense of it, what we're trying to do is not possible.
Yeah,
like,
it's not.
Yeah, it's not possible to do it without amplifying the error. But anybody have any other question?
So the work done must be done.
The work done has to. The work done has to be done, but you're trying to save yourself. Like, come on, like you're saving yourself. You're selfish in this
But at the
case.
end of the day,
Right.
it's likely still the same process because first you have 15 apples literally and the program could just run an iteration through the 15 and pick the red one out. But now you are exploding it to 15,000 because of the fact that I'm trying to check through one after the other, which is still the same first step you're trying to do, check one after the other. And when it sees a red, it now explodes and be like, so it's just like that second example you gave. Where is where is the chance of
I think
So
the question is trying to
it's-
ask what is the essence of the error amplification if we have a function that could just run a
Yeah, that
sequence
just run
and check
and
all
it
of
sees
them
And
one,
check.
get the red one.
You still
Listen, I'm
you still want to be able to. You still want to do your check. The function does its thing, right? But you are still going to pick, right? So the function does its thing and gives you back a blown up number of apples, but you're still going to do your check. Yes.
So my concern is, you said if the both apples are green, it gives you like all green. But if one of the apples is red and the other is green, So the function just continue giving you, if you get the first green, it gives you green.
No, it doesn't. It doesn't duplicate until it have checked all of them.
Okay.
So if it's as it's checking them,
Yeah.
if it finishes like checking them and it doesn't see a red, that's when it does a duplication.
Okay.
So
In a case where there's red.
in the case where there's red,
Yeah.
it checks the first.
Okay.
Say the first is green,
Okay.
it doesn't do anything. It checks the second. Say the second is green,
Yeah.
it doesn't do anything. It checks the third.
Okay.
If the third is green, let's say there are 5 apples.
Yeah.
If the third is green, it doesn't do anything. If the fourth is green, it doesn't do anything.
Okay.
If the fifth is now red,
Yeah.
it amplifies the red.
Okay. So now on this other side of the sequence, if it doesn't do anything when it gets a green, why are we having one extra green? Is it like it's moving the green it got from this side to the other side, then it continues amplifying only red?
Okay, like
It's a problem
it's
with imaging, right?
no, it's not a problem with the imaging. We still have that original sequence.
Okay.
So we're adding to the original sequence, not that we're scrapping the original sequence.
Okay.
So we are amplifying, we're adding to the original sequence. Not that we're totally scrapping the original sequence.
So how does this differ from method 2?
For method 2.
The method 2 you explain where you the work done is 3. The second
Yeah.
this that you explained, the work done was 3
It was.
because the first one was red, second one was red, the third one was red.
Yeah.
Making the work done 3. So how does this, because we are trying to bring it in a human sense where we have someone trying to know what is there without actually seeing what is there. So how does this now differ from, because we just only exploded the red apples and stuff. So how does it differ?
In that case, like, I don't know if I got your question well, but let me just explain, like, based on what I understood from your question. So, in that case, the function is what does that 3 checks, right? And when the function gets to the 3rd check, the function doesn't need to check the remaining 15,
Yes.
right?
Yes.
So the function just duplicates the original sequence and then adds red.
Oh, so the check will now be done on the other one. Sorry.
Yeah, on the blown up
On
one.
the blown up one.
Yes.
Oh,
Sorry.
nice.
The goal of the function, the goal of this function is to detect the red apple, right?
And amplify.
And amplify.
Exactly. That is just what it's
When
doing.
you detect it, stop, then just amplify.
Amplify,
But
exactly.
if it is still green, it keeps on checking, right?
Yes, it keeps on checking.
So that increases our chances of finding when we want to make our pick now. Now that it's blown up, it increases our chances of finding the bad one.
Yes.
Sorry. So that means it means that for every let's say sample or collection, if there is a red apple and it is probably in the middle, it has used the time to get
Yeah, it increases the time to find the red apple, which means it will do more work until it gets to that red apple.
And with this method, the probability is 100%.
With this method,
Yeah, like the probability is definitely 100%.
It's not though.
I apologize,
No,
but
it's not.
in as much as we have that factor of not checking everything, we lose the ability to have 100% certainty. We lose it.
Because why I said so, or why I made that assumption was, for instance, talking about 5 apples that you used just now. If all are green, it's going to check through all greens and then explode that everything is green. So since we are not checking the original iteration, we are checking the blown up baskets. So definitely any pick one make is going to be green. That's 100%. Now, if out of that 5 now, say the 4th one is red. Now it checks first green, and then the 4th one happens to be red. It's going to stop at that point and then explode the red into other baskets. Now the original iteration is duplicated, but the other basket get that red. So since we are not checking the original iteration, we are checking the other baskets. We are definitely going to pick red, no matter what.
That's what you think, like,
Sorry,
okay,
I think I can answer it.
okay, please.
The reason why we talked about probability is to test our confidence level. So since this model or function, we do that for us that for certainty there is red. We don't need to worry about probability anymore. Am I right?
We still
the
need to
point
worry about
the point is that let's say we have 5 apples and the third is red and the remaining 2 is, so when we use this model or function, immediately it gets to the third whatever, it amplifies it and it stops reading the remaining. Even though maybe let's say we have 6 now and the 6th is red too. So we don't have to worry about this the 6.
But we're going to duplicate the initial sequence.
Yeah, so we still have.
So we still have that.
So the main sequence is preserved, right?
Yes, the main sequence is.
So you have to obviously see picking green or black.
Yes.
So the main essence of this is to increase our chances of selecting a red. Because I remember you said when we have more green, it's much harder to select
A red.
find the error. So when we have the error behind, we can easily pick
Pick.
them.
Yes. So making it easy for us to pick a red does not mean we have 100% certainty. In as much as we are doing just one pick, we have lost the ability to have 100% certainty. The only way we can have 100% certainty is if we check every apple in the sequence, whether we blow it up or we don't blow it up. The only way we can get 100% certainty is if we check all the apples in the sequence. But once we say we want to reduce our amount, the amount of work done by reducing the number of checks, we have lost the ability to have 100%. We can have 99.99999999999, so wherever 9 wants to go, but we can't have 100%.
Yeah, I think probably I'm not getting the description I put in my head also. Okay, like, let me just print it out. This is what I have in my head. You have a basket, has 15 apples.
Let's use 5.
Okay,
So
it
that,
has 5 apples.
yeah.
Now, using this amplification method, it checks, let's say the fourth one is red. Now, it checks, or let's say it's all green first. It checks the first, second, third, fourth, fifth, and sees that they're all green. Then it kind of creates like 1,000 baskets, and then puts apples in all of them, but all apples that are in those baskets that have been created are green, showing
So,
that everything is green. Is that not the amplification that, like,
this way you're talking about it, you're seeming to scrap the original
yeah,
sequence,
I
but
thought
we're not scrapping it.
also the original sequence is
It's
still
still part of the 1,000, or it's still part of the 10,000 or
and it can be
15,000.
part of what can be checked.
Yes, and it can be part of what can be checked.
There's a task, there's 5 buttons. There's one that is like, so what the function is doing is just picking one, and when you see it there, just go and carry it, put it inside the sound, and chase it. So your probability of just picking it is increased. Yeah.
So is that not, are we not messing with the stuff like that?
No, I'm not messing with stuff. It's still inside.
No.
The 5 buttons will be there.
According to the 10 number, they say if any apple in the small sequence is red, then the additional apples in the bigger sequence are also red. Why?
That is the essence of the function.
Like, okay, now just like I'm saying that, let's say we are in a bakery, right? We're in a bakery, there are 100 breads. Let's say there are 100 breads. Like, about 2 or 4, let's say like 5 have least intentions. So now we are not arranging it in let's say the algorithm we are using, let's use an array, right? So from left to right? So 1, 2, 3. So the first bread is good, the second bread is good. Now, the third bread was not good. All the third bread was not good, automatically it amplifies for the
If the third bread was not good,
yes,
we are going to carry those 100 breads that were in the bakery
yes.
and put in the van. Those 100 breads, we are going to put them in the van, and then we are going to add extra.
Extra 1,000 baht.
Extra 1,000 bad bread. Yes. Nice. We are amplifying. So, sorry, please, can we reduce the noise? Okay. Sorry, after him.
So my own question is, I feel where this problem is coming from error applications, it should be like perfect amplification. Because we are amplifying where our success is.
We're amplifying our success rates by amplifying our ability to detect the error. So what you're saying is just similar to the 7% and 93% thing, right? So if you increase your ability to detect the okay, so they're override. Okay, so if we increase our probability of detecting a red apple, that means we increase our probability of not going to prison, right? So okay, I don't know if
I get what you are saying, I get it, but I feel it should be success amplification. Because
okay,
now
that will make
if
it
you
easier
want-
for people to
yes, because if you want
understand.
it to be green now, it is green that will increase, right?
If you want to pick,
A green apple. If you pick a green apple,
No, but-
amplify.
But
I think
but
we are trying to
but I think
No.
the end point is that we are looking for the error.
exactly.
So we are
Yeah,
trying
it's
to
the error that we are
amplify-
looking
we are trying
for.
to explode the
If you
error.
want to pick the green, that means green is the error.
And yes, amplify
Okay,
what we know.
yeah.
We don't find the red. Why are you still
Our success to pick the error. That's the point.
Sorry. Sorry, let him.
I just want to confirm, like, so in the larger sequence now, larger sequence, is it a random sequence, like the error and everything there, is it random, or is it just going to be from the smaller sequence, then appending it to the application?
Yeah, it's the smaller sequence appended with the amplification. We're still going to see like an
So my
example.
question is really is, why do we have the red apple, the red apple before the green?
Oh,
I said that.
yeah, it's an image. Sorry. It's an image stuff. But we can as well think of this as a basket, right?
So that's what I was asking, whether it's a randomized stuff, like.
Yeah, if it's a basket, you can think of it as randomized. We're just using it sequentially here so that we can visualize. Yeah. So it's as if it's a bag, right? So the bag can shake and they can. But when you're dipping your hand in and you're bringing it out, it automatically starts taking a sequence. Right. Like, is everybody kind of? It may not be 100% clear, but are we together? Okay. Okay, so let's now revisit the check one protocol. That is protocol where we do just one check. So, say, still the same example, right? We have 14 apples and we want to do just one check. What is the total work that's going to be done in this case? One, right? Okay. But before then, let's blow things up. So we give that sequence of 15 apples to the error amplification function. It goes through the apples, sees an apple at index, say index, let's say 11, right, or 12, and then based on that, it amplifies the error. So now this is the basket that we want to dip our hand into now, right? Yeah, thank you. So in this case, we are doing just one check, right? So work done is 1. So if there is a bad apple now, what is our chance of detecting it? If there is a red apple in this sequence.
The red apple, 100%.
No.
99%.
No.
Okay,
Yeah. So we amplify it to get 14,000 apples, right? Out of those 14,000 apples, we have 13 that are green. 13 green apples and about 13,987 red apples, right? So we can see that we still have that initial sequence, which is like this first block, right? And then we amplify. So what will be our probability?
99.9.
Yeah, actually 99.9. So even if there was just one red apple or one green apple, even if there was just one green apple in the entire sequence, right, we are not still going to have 100% certainty. Like if just the first apple was green and the other like 13,999 were red, we are not still going to have like 100% certainty. Do we agree?
Yes.
Because of that one.
I have a question. What if the basket was bigger? Let's say it's a basket of 14,000 apples, right? And we have like we have just one red apple with 14,000, and you go through the whole basket and you pick one red and amplifies it to 14,000, which is very close to the other green.
Okay, so you're saying, say we amplify it, but we don't amplify it up to.
So what I want to be sure, the amplification, is it fixed, or is there like a way whereby you say if like you do like times 14 of what was the other basket?
The amplification would be 40 million.
Okay, times 1,000.
Yeah.
Okay, I get it.
Times 1,000. No, it's not fixed. You can decide. Yes. You can decide how much you want to amplify the error, right? But you know that if you're amplifying the error, it's still you that will carry the 14 million. You're still the person that will carry all the baskets, right? So yeah, you're reducing the chances of you going to prison.
But there's still a chance of going to prison.
Yeah, there's still a chance.
But there's still a chance.
There's still a chance.
There's a chance of failure.
How about if you
But that chance of failure, sorry. That chance of failure, once you see that red, you're discarding the whole basket.
Yes, I know, but there's still a chance that you still put your hand
And pick a green. Yes, it's still possible.
Very, very low.
Yes.
what if the basket has fallen?
No, you still need to amplify. So if all of them are red, once the amplification function checks the first, it just blows it up. So the amplification function does like, let's say, yeah. You're not still getting 100%. Okay, sorry. Yeah, I get it. Yeah. Like, we don't know. So, like, I hope everybody is taking note of, like, the different components of all these discussions, because all those different components are applied in ZK, like like building of ZK protocols. All those different components, like the picking of one apple is like a protocol. The error amplification is like all those different parts. The function that does the error amplification, picking of one apple. So, like, even what he talked about, where he said, where we can we give that basket of apple to many farmers to help us check, right? It sounds abstract, but all these are still various concepts with respect to. Okay, that's why, like, the idea is for us to understand this thing very well, so that we can easily see it anywhere. We don't necessarily need to see it just in ZK per se, because, like, after this class, or after this the training period, say at the end of 3 months, it's our hope that some of you here, like, come together and build, say, you can come up with your own protocol. You can come up with your own protocol and optimize for something that is missing in this space. That's why we are trying to go this. That's why we're trying to go this there. Because if you understand how everything comes together, it will be easier for you to know, okay, this thing is currently done this way. It can also be done this way. So please, people should be taking note of, like, the different concepts we're talking about.
So I want to ask, the essence of us having this amplification is so we can have 99.9% chance.
Yeah, to increase our confidence level.
But it won't be at all times that we are having 99.9.
No. It's possible that we can have even like 80, 87, or maybe 70 something. It's still possible. But in this case now,
it will always be higher than.
Yeah, it's always be higher than if you just do it without amplifying the error. It will always be higher.
And so, should it be that way, right? Because if you're always going to do the error application, there should be a certainty that if you do the error application, you should always get 99% chance. So, what scenarios now are you going to get to like 87% or 78%? So I think it still goes back to what Cass is saying, right? On how you scale it up. Because I think you scale it up and you don't scale it to
so much.
Exactly. That's when you can then start saying,
like, this, what we're doing now is basically, like, when we look into the stack protocol, it's kind of almost the same thing. Like, this is almost, you can basically think of this as the stack protocol. I won't say the stack protocol, but maybe like the initial part of the stack protocol. So, the whole concept of error amplification and all. So, there's what they call the blow-up factor. Yeah. Our CS students, did you guys do anything on, like, in coding theory? Do you guys do anything on, say, the rate of a code, or did you guys do coding theory? For those that did CS. Huh? Okay. Okay. Well, we're going to be talking about those things. Yeah. Sorry, the noise, please. The noise. So we're going to be talking about those things. So there's what they call the rate of a code, and there's what they call the blow-up factor. So the blow-up factor is basically how you intend to. In this case, our blow-up factor is, you can think of our blow-up factor as like 1,000, right? But increasing the blow-up factor also has like its downsides. It's sure, like at the moment, for I don't know, maybe most of you guys haven't really looked into the space at all, but like they are currently trying to optimize for the rate of the code. Let's say trying to reduce the rate, because the rate and the blow-up factor are proportional, inversely proportional. So if you have a blow-up factor of 2, right? So you're going from, let's say, 14 to 28, right? Your probability will be lesser. If you have a blow-up factor of 1,000, your probability will be higher, right? But the thing now is, as you're blowing up, you also need to account for the extra baskets that you're filling, the size, exactly. Like you can think of it like, if you have, let's just think about it in the sense of, say you want to download a picture, right, from the internet. A picture of, let's say, 5 KB, you'll be able to download it faster, right? But then a picture of 50 megabytes, if it exists, it should, right? It will take more time, right? So you can think of the blow-up factor of 2 as, let's say, the basket with 28 apples. You can think of it as like as the picture of 5 kilobytes, right? And then the one with the blow-up factor of 1,000, let's say the 14,000 apples, you can think of it as a picture of like 50 megabytes, right? So you need to do more work, or you need to have more space, right, where you're dealing with a bigger blow-up factor.
But in cases like this, which will you prefer? Let's say, okay, a picture of lower bytes with poor quality that you might see the
pixels. Yeah.
Or a picture of bigger quality that is very clear, that you can actually, that you won't have to strain your eyes. Then relating it to the whole subject stuff. Okay, you have a smaller blood factor with higher level of breach. That is, security factor is very low,
Yeah.
and the one with the higher blood factor that has higher security. So which will you choose in a case like this?
Okay. Like, let me just try to relate it to ZK. I'll pick depending on what I'm trying to optimize for. Like, there's what they call, because in ZK, I'm sure most of us have heard about like the prover and the verifier, right? So you may be trying to optimize for prover speed, right? Like maybe trying to optimize for prover time, or you may be trying to optimize for verifier's time. Like this is I'm saying now, like I won't call them subfields in ZK, but they are like a whole paradigm on their own, right? And it's good we take note of these things. So you may be trying to optimize for prover speed or verifier speed. Maybe try to optimize for prover space or verifier space. So the space, with respect to these apples, you can think of it as like more apples will contain like a bigger room, right? But you can use a smaller room for smaller, like after blowing up if you don't blow up too much, everything can be contained in a smaller room, right? And you can think of those rooms as your device RAM, right? That is processing all these things, right? So it depends on what you're trying to optimize for. So you may be optimizing for either prover time or prover space, or you may be optimizing for verifier time or verifier space. So that will now like determine what what you can use as your blow factor.
On the error application, I think we need to say something like trying to reduce that workload. So for this error application, we have more. So is it because we are trying to like focus on being more having more accuracy, so that
I would say
so that more just because we need more accuracy. Because now that's to get the count.
no, you're not checking all of them in the 14,000 sequence. You're checking just one,
Yeah.
right? Or they is the total number. Okay, like to get the 13,900 and this thing, right? So the error amplification function that does the counting will tell you that, right? So you're still on your own, you're still doing just that one check, right? But the error amplification function is what does like checks all of them, checks the counts, and then like give you all those information. Eh? So yeah. So like does it may not be very clear, but are we together? Any other questions so far?
So this error amplification system, let's take for instance, like an actual production environment and whatnot. So that means we are trusting that this system does work. We actually want.
Once.
So we are trusting.
Yeah, we're trusting it.
So how does it know the errors? Are we telling it to be good or wrong?
No, we'll get to that. We'll get to that point. Like how it knows which one is bad, and we'll get to that point. Okay, so all of us agree that the probability of detecting a bad apple here is 99%, right? Okay, so what have we learned so far? We have learned that we can verify a very large statement by doing very little amount of work, right? So, because we can also achieve this without losing confidence in the results. I could have found we may not have like 100% certainty, but we can have something close to 100, 99.9, very close.
So that we're not being 100%, should not be worried.
It should be worrying, but not so worrying, right? Not because it's still possible that you can pick that one green, like that your one check. Maybe there's just one green in the 14,000, and unfortunately, with all the randomness in the world and everything, you still go and pick it. It's still possible, right? So in that case, it's worrying, you get. But based on probability, it will be difficult. So we are just relying on probability now. We know that it's not 100%, but since it's very close to, we can decide to. this thing you just said, it's also like a concept because they have like proofs and arguments of knowledge, right? So they have proofs. Proofs are like 100%, 100% certainty. Arguments of knowledge are like when you're talking about arguments of knowledge, you have lost. Like if it's not 100% certain again. So you're just kind of like arguing. So we can see that computation is now asymmetric. One party can do more work so that another party can do very little work. The party doing more work in this case is the error amplification function, right? That blows up the error. Us, in the case that does very little work, just to pick one apple to check, right? So this is kind of like the whole essence of ZK, right? We are trying to do less work. Okay, there is this example they usually use. Now we have a supercomputer, and you have like, let's say, a smaller device that wants to monitor a supercomputer, right? So you can have a function, a very big function that you want to run, and your small computer cannot run it, right? But you have a friend that has a supercomputer, and you give that your function to that your friend to run it on the person's supercomputer. Since you know the person has a supercomputer, you may want to blindly trust the person, right? But it's not always good to blindly trust like that, because since the person knows, the person may not want to maybe on the person's generator to actually run that function, right? The person may just say, okay, you've given me the function, right? The answer is 5, right? The person just tells you the answer is 5. And because the person has a supercomputer, you actually think the person ran the function. Meanwhile, the person didn't. The person just gave you a random answer. So the essence of, like, in this case, ZK, is to verify that the person actually did the computation. We're going to get to that. Just for now, just look at it like as a high level stuff. So we want to verify, like based on the answer the person gave us, we want to verify that the person actually did the computation without just giving us a random answer.
Because somehow the concept is still centralized, right?
In what?
We are no longer dealing with decentralization, like in blockchain, since we are trusting somebody with a central supercomputer to run stuff for us.
No, like in this case, we're not talking like forget about decentralization. Like forget about decentralization. Okay, so this is like outside the blockchain. Yeah, but it's applied. It's like a field on its own that is now applied in the blockchain scenario. So just forget about decentralization for now. So why is this all important? Computationally intensive tasks require a lot of computational resources to be able to carry them out, right? That's why most people rely on computer servers. How can someone with a mobile phone verify that a server actually performed the computation correctly without doing the work? That's the question. So randomness helps us achieve this, right? So we can tell a server to write out every step it took to perform the computation. Like that our function that we gave the supercomputer, right? We can tell it, like when you're running this function, every step, write out the answer for like every step in the sequence of the computation, right? And that is called, usually called in this space, that's usually called the trace. Yes. So, not stack trace, but it's just a trace. Eh? Okay, say like, okay. So the stack then, stack trace, like it's talking about one specific data structure. So, and then like after the supercomputer like generates the trace, we can then check the trace at a handful of points and then be convinced that the computation was done correctly. Can we relate this to the apples scenario? Right? Can anybody like just help us relate this to the apple scenario? Okay.
The evidence of the trace of the trace in the apple that
The trace.
Yeah, that's the evidence.
Yeah, that's the evidence that it works.
Trace. Then we check the trace. You know that check the original apple, we check the trace. The original
Okay.
basket, check the trace. Those seven apples. That's the bad apples.
It's close, very close. Sorry.
I think the trace is after the application, and then when you check the traces, you doing the check, but maybe more than once.
Okay, let me just see everybody's view first.
So I think the trace would be
For, the function that does the amplification checks each of the apples until it gets to a red. So the trace would basically be like, okay, possibly like have a way to, when you check a green, you like mark that this is a green, like you keep count of the number of greens, like, and or then when you get to the red, you amplify it and also keep like a way of logging your steps at every point in time to the point where you did the amplification. Then, and I think that would be like the trace. Then moving it over to the other function that like does the verification, like picking the whole stuff. So the trace is like logging all the steps from point A to point Z. I don't know that.
Okay. Let me hear you.
Yeah, it was kind of like that was what I was going to explain of picking when the error amplification program takes a green to log that it picked a green, then to the point where it has done the blow up, and then the point where it has picked from the original sequence and adds the amplified error to it. So it lets you know that it actually did the work and you can verify through the trace.
Okay. Oh, let me just. In this case, like error amplification is not. In this sentence, we have not even talked about error amplification, right? Because the server is the person who wants to do the work, right? So the server is the person that is meant to bring the apples. Let's just think about it that way. So the trace is basically the original set of apples. You can think of it that way. So we're telling him run this function, and for every step, give us the value at that step. Right? So the server is going to run that function, and for every step, the server is going to give us a value for that step. So after running the function, those set of values that the server gives us is the original basket of apples. You can think of it that way. I don't know if it makes sense. Like, we can think of the trace as the original set of apples. Because the server, we want the server to prove that it did the computation correctly, right? And for it to prove that, we told it, give us all the values for each of the steps of the computation. So when the server is running the computation, it's logging those values. Like for every step of the computation, it's logging certain values. Right. So after it finishes the computation. It gives us like a record of all the values for each step of the computation. And then when we take that original trace, we can amplify it. So we amplify it so that if there is a step that the server lied about, if the server lied about just one step, then when we amplify it, more steps will be corrupted. Let's say a program that is meant to have like 50 steps. A program is meant to have like 50 steps when you execute it. We tell the server, execute this program. So what we're expecting is, say, an array of 50 values from the server. A value for each step of the execution. Does it make sense up to this point? So after the server has given us that array of 50 values, we now need to amplify those 50 values. So if we want to use a block factor of 4, we amplify that array to how many? To 200. Right? Yeah? Yes, exactly. The lie. So if there is just one point in that computation that, say, the server lied about, the remaining 150 points will be wrong. The values will be wrong. Does it make sense up to this point? Yeah. Then us now as the verifier, because we want to verify that the server did the work correctly, it's now our duty to now pick one value from the 200 values that we got after amplifying the error, and then check, like based on some mathematical checks, check if that value for that index in the computational step is actually correct or wrong. Just think of it like abstractly, but like at a high level, this is kind of what's happened.
So, if I understand correctly, let's say we are giving the server is giving set of 50 values of, let's say, 50 array of 50 values, right? Assuming, like, going back to the Apple scenario, let's say green is X and red is Y. So if we have like 30 green, that we have X in 30 places, and 20 red, we have Y in 20 places. Now if the server peradventure skips any part, let's say the server skips 10 of the processes and give us like 20x before the server got a Y and amplifies it, then from the verifier side is going to like show that the server lied to us one way or the other.
Yes. So I don't know if like does it make sense up to this point? But does it make sense? Okay, you're not clear. Do you have any? Can you watch the? Okay, yes.
So you said the trace now. Will the trace be like the 14 apples that you gave us?
Yes.
And then you give those 14 apples to the supercomputer to go through.
No. It's a supercomputer that is giving us the 14 apples. Yes. See, like there.
Okay, can we maybe relate it to, because I think the initial example was the phone and the server, right? So there any way we can what exactly are you trying to verify from the server? How are
Okay,
we going to
so
verify that
so we have a function. Let's say we have an array of 1 to 50, right? And we wrote a function that loops through that array and returns true or false, right? And what we want to do is to loop through that array and return true if a value in that array is less than 5, right? So that means after looping through that array, we are going to have another array, right? With true, false, true, false, true, false, true, false, right? So we write a program. We write a program that does the looping. For each step of that program, it's meant to return a true or a false, right? But let's say our computer is, let's say, a watch, right? And we can't run that program on our watch, right? So we want somebody with a laptop to run that program for us and give us an array of true, false, true, false, true, false, right? So we can give the person the program to run the program. The program is the computation, right? And we want a result, which is that array of true, false, true, false. Right? We cannot run the program on our watch, but somebody with a laptop can run the program. So we give the person the program. It's possible that when we give the person that program to run, the person can just create a random array and just fill in false, 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 false. You get? And give it back to us without the person running the program. But that's not what we want, right? We want a situation where after the person has given us that array of true, false, we are able to verify that the person actually ran that program without us rerunning the program. Right. So what we do is, okay, we tell the person, take the program, run it, and give us the result, which is that array of true, false, true, false. So once we have that array of true, false, we can pass it through an error amplification function, right? That error amplification function actually checks if the number in the array is less than 5, right? And then checks if it corresponds with what the result we got is, right? So if it corresponds, that is a green apple, right? We can think of this is the error amplification function now checking. And if it corresponds, that is a green apple, right? We go to the next step or the next number in the array, we check. If it corresponds, it's a green apple. If it gets to a point where, let's say, the answer is meant to be true, but in the array the person gave us, it was false, it will just amplify false, right? And then the error amplification function gives us that blown up trace. So us now, we can pick one random value from that blown up trace, right? And we can check if, like, for the blown up trace, let's say it's going to add like some extra numbers, some extra random numbers, and then check if, like, and then like if it finds a false, like if it finds an error, for those random numbers it's going to add. Even if those numbers are less than 5, it's just going to add false, 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 false. Does it make sense? So when it's now our time to verify, if we come and we pick a random number, luckily if we pick from like the extended point, we are going to pick a false. Or the random number that we are going to pick, if we check that random number and see that it's like less than 5, or how do I put it? Like from the extended numbers, if we pick a number there and we check that number is less than 5, then we're also going to check the result and realize the true false, true false. Maybe I'm going to, I think this may be something we may need to like write, but I'm not prepared for writing it today.
So I think it's safe to go back to the caching position of where you have to check.
Yes, okay, yeah, so that is what does the, like that is the error amplification
Yes,
side
check
of
so that you
things.
can correctly check them for the number that you or not.
Yeah, yeah. So
And you
But
also
doesn't
said,
that
you
make
also
us
said the
dependent?
supercomputer is the one giving us some results. Or in this case, the supercomputer is the one giving us the array of 1 to 50.
no.
It's not.
No, the supercomputer is the one giving us
The results of
the result of true false, true false.
So,
And
the ones giving it the 1 to 50.
yeah, we're the ones giving it the 1 to 50. Yeah. Yeah, for it to run. We can think of that as the inputs to the program. Yes, the trace is not necessarily the output. I don't want us to go into that part yet. Let's take it step by step. We are going to understand why the trace is not necessarily the output. So the program can have an input and an output and still have a trace. The trace is not necessarily the output. I think I may be going a whole lot deeper than I should in this talk.
So is this not making us dependent on something we are trying to something we are trying to, we are depending, yes, we are depending on something we are trying to verify. Like in the sense of the apples, for instance. Now the apples, now we give the apples to a computer and say, okay, check if there's any red apple there. And then it gives us a trace that, okay, I checked through and I got an apple in the 14th iteration. And then that trace now, we now verify and say, okay, that passed through an error identification, and then it's able to now blow it up and stuff. What if the computer itself now does not even go through, does not iterate through the whole apples itself and just goes through maybe the good ones and gives us a trace of something good at the end of the day? I will not dependent on him whenever we are amplifying, it's just a result of what he's giving us.
But that is where like
how can we trust the trace we are getting from it? So we cannot be that we are still going back to check with the input in the first place.
that is where the maths side of things comes in. Yeah. So we're not going to go into that now. We're going to get to that point. But that's where the maths part of things comes in. That we're able to verify, like the verifier is able to verify both with the prover's data and with some information the verifier already knows. Yes. I hope I did not like get some people confused.
Now you did.
I got right. I apologize for that. So let's just forget about everything we've said. Okay. And let's just come back to this. Huh? Let's proceed, right? Okay, so we can tell the server to write out every step it took to perform the computation, and then check that trace at a handful of points, and then be convinced that the computation was done correctly. So polynomials for error amplification. I still have a long way.
In the last slide, related to like the red apple and we started from red apple and all of a sudden we just switched. So what's like related to that? What is the trace in that case? And we just give like
What's the trace in which of the examples? The red and the green apple. Okay, in the case of the red and the green apple, the trace is the original basket. Let's say those 14 apples. Yeah, so that's what you can think of as the trace.
What is the output?
The outputs. So the outputs in that case, let's say we are trying to get a true or a false if the basket has a red apple or not, right? So we can think of that as the outputs.
Sorry, if that's the trace, we gave the basket to, is it that we don't know the actual content of the basket before giving it to the server to like run its computation? Because if what the server is giving back to us is the trace, it's basically like giving us what we give back to it. So, and the server giving us what we give back, giving us what we give to it, without any extra constraints. I don't know why that is the case.
No, like there are different, like it's not directly, like you can't equate the apple and basket examples directly to this. So it's as if we just took out a portion of this, like the computational representation, and we just brought out, we just abstracted it to bring out that apple scenario just to help us understand some things, not the entire. The apple scenario does not cover the entire process. You get. The essence of that apple example was just to help us understand what error amplification. Yeah, it was just to lead us to error amplification and how it affects probability. You get. So like that on its own is like the error amplification. You can think of it like as a tool that can be applied anywhere, right? So it's if you understand what went on in the whole apple scenario, you should be able to apply that knowledge, say in this computational scenario now. You get. So it's not as if like it's a direct representation. It's just like an abstract thing to help us understand that concept.
So is it in the proving stage or verifying stage as application stage?
That's
Is it the proving stage or verification stage that we use
the amplification in the proving. Yes.
So, is it right to say we just kind of like you say, okay, we have bags of apples and stuff, and we just kind of like take a bag and then pass it to the system and say, okay, check through this bag for me. Like we are not seeing the content and stuff. So it is the system now that is now kind of like saying, okay, green, green, red, and stuff like that. Now, if in that case, my question now is, will that system now, will it still check through everything in that basket, or will it stop at that wrong results or wrong input that you?
So I think the way you're going about your question, you're still trying to link the whole computational thing with the apples and
No, I'm trying to do a kind of calculation, like even if we are passing in a kind of computation, like calculation, and we say, okay, this value, we should, if it does not give this value, then this thing is wrong and stuff like that. So is it like when it's okay, it will solve through, if it's a kind of equation, it will solve through before getting the result in it.
Are you okay? Okay.
I want to say something.
Yeah, please.
So I think we should post the entirety of the weather plan for now. So what I'm thinking is the apples before they get to the farmer, maybe there's like a way of something, before they get to the farmer, before you get to the market, they pass through a computer. This computer marks the apples that have been checked. Like maybe like a marker or something. Then if the farmer picks any apple randomly and check if it has a mark on it, the farmer should be able to pick any apple and check if it has a mark on it. If an unmarked apple gets picked, we automatically assume that it is totally bad and it is wrong. So that amplifies the fact that he didn't check the apple, he didn't check one apple they had. That means that's like a bad apple. The apple that they get checked is a bad apple, so it amplifies it.
Yeah, I think you can also think of it that way. I like the example you used because you kind of like abstracted the whole, like you kind of like brought out an example from what we already, like the apples and oranges example. So I think you're right, and I think we should just like if we're able to just understand the whole what we're trying to achieve. We're trying to detect error and amplify error. Finish. That was just the major reason for us using the apples and oranges example. Right. So I think let's just think about it that way and take it in our head as a concept. The goal after this will be like now drawing lines, drawing connections, right? Like drawing those lines and connections is what will help us to fully like internalize this stuff, and like we can basically see abstract examples where these things can be applied, right? And that is what like enables creativity, right? So just understand what was the problem, what were we trying to solve, what process did we use to solve it. In the apples example, the problem was detecting a bad apple, and what we used to increase our chances was error amplification. We used error amplification to increase our chances, right? So error amplification was the tool we used to increase our chances, right? So I think understanding that concept that way, if we now think about it with respect, we can now like think about it like in other areas too. Like say for the computation aspect, the apples, we're trying to detect if one step in the computation was wrong. We use error amplification to amplify, like if there's any error in that in the computational steps, we use error amplification to amplify it, and then like to increase our chances of detecting if any step in the computation was wrong. So for now, let's just think about it like at that high level.
Sorry, I'm trying to actually make where randomness comes in.
The randomness.
Because randomness supposed to achieve this. And from what you explained from the computational trees, it's more of we are tracing, let me just as a split it.
Yeah.
Just tracing the whole, or logging the whole this thing. But the way I relate it to my is, I have a function do this, and I got my results, but to check the steps that took place during my final answer, maybe I console log at different steps, and I'm saying, okay, this is how everything laid out before I arrive at this. So I kind of place the trace that way. So when the end of randomness
Coming. Yeah, I like the question. When randomness comes in is when we want to, let's say when the verifier wants to pick a point to check. If the verifier always checks the first, it's possible to put all the red, like let's say in the apple scenario, put all the red apples down and put green apples, like when we're filling the baskets, right? We put all the red apples down and put green apples on top because we know that the verifier always picks the first one, right? But where randomness comes in is that the verifier picks a point at random. So the verifier puts the verifier's hand, shakes the basket, and picks out one. So since the prover does not know the exact one that the verifier is going to pick, the prover will try to behave himself, right? I don't know if it answers
I
your
think
question.
it's possible to repeat that same process to increase the verifier's confidence in that computation.
So
Like
to repeat,
to repeat
yes,
it, like
yes.
pick one,
Then pick another
pick
one.
another one.
Yes, exactly. It is. And it's also like applied in like ZK, so they also use that concept, like multiple checks. Yes. So are all of us like comfortable up to this point? Okay, so so let's just rush through polynomials for error amplification. When we get to this summary, we'll take a break and let's say maybe 5-10 minutes break. Then we come back for this second part. Hope that's okay. Okay, so polynomials for error amplification. That error amplification function we've been hearing, the one that checks everything and all. Yeah. So we can use polynomials for it. So we can encode the computation as a polynomial such that the evaluation of that polynomial at a number will give us the result of the computation at that number. Right? So where the number is a computational step. So like we have an array, right, that contains all the computational steps, right? And we take that array and we do a polynomial interpolation to get a polynomial. Do we look into polynomial interpolation and evaluation over the night? We're still going to look at it. So for now, just take it as a black box. Alright. So we have the results array that the server sends. Right? We take it, we encode it as a polynomial. Right? So what we want is that if we evaluate that polynomial at 1, we get the answer of the first computational step.
So basically, this thing now is for verifying, right?
No, it's still like,
Still improving.
yeah, still improving. So if we evaluate that polynomial at 1, we get the answer of the first computational step. If we evaluate the polynomial at 5, we get the answer of the 5th computational step. So after we get all the computational steps, we interpolate it to get a polynomial. That polynomial, we can evaluate that polynomial at any point. Does it make sense up to this point? Okay. Let's say we have all the result of all the computational steps, right? We can use a polynomial for error amplification. How? If we have just the result of all the computational steps, it's finite, right? Let's say if it was 50 computational steps, that means that result will be just 50, an array of 50 values, right? An array of 50 values, an array of, or a basket of 50 apples. You can think of it that way too. Right. So now we have the array of 50 values. We interpolate it to get a polynomial. We're going to look at polynomial interpolation, but for now just look at it like as a black box. So polynomial interpolation basically enables us to go from the evaluations of a polynomial to its coefficients, right? So you have an array of the evaluations of a polynomial, then you want to go to the coefficient form of that polynomial, such that when you have the coefficient form, if you evaluate it at a point, it will give you an evaluation point. We're still going to.
Sorry, we don't know. That means we don't know the polynomial for the error at first.
Yeah, you don't know it because the results can be anything. It can be random, so you can't just know it, right? So you don't know it. So it's when you, well, we're still going to, when we talk about polynomials, we're still going to talk about like different ways of representing a polynomial. You can represent a polynomial in the coefficient form. You can represent it in the evaluation form. Right. So we can think of that trace, the computational trace, as the evaluations of a certain polynomial, but we don't know the polynomial. Right. So we now interpolate that polynomial to get, we now interpolate those values, to get a polynomial. Does it make sense up to this point? Huh? Please, if it doesn't, ask.
So we interpolate the results that the server sends to get the polynomial.
To get a polynomial.
Polynomial, will it be for the error amplification?
Yeah, we can use the polynomial for error amplification. Why? Because you can evaluate a polynomial at any point. I don't know if it makes sense. So, okay, let's look at this now. So, this is the original set of apples, right? So, we are looking for a polynomial such that if we evaluate that polynomial, at 1, if we evaluate that polynomial, we are looking for a polynomial f, right? So that if we evaluate it at 1, we get this apple, this particular apple, right? If we evaluate it at 5, we get this particular apple, right? If we evaluate it at 15, we get that last apple. That's the polynomial that we're looking for. We don't care about and for the other points, if we evaluate it, we don't care about what it evaluates to at those other points. At points outside 15. Right. we don't care. But does it make sense? It makes sense, right? So, why we are looking for that polynomial is because we want to use it for error amplification. What does error amplification do? It blows things up, right? So error amplification is the only thing that enables us to pick an apple that, let's say we started with an initial sequence of 14. It's possible for us to pick an apple that is 1000. It's not in the original initial sequence, right? But when we amplify things, it's now part of the like sequence, right? So, okay, this is basically what I'm talking about. So if you evaluate it at 4, you get this particular apple. If you evaluate it at 12, we get the numbers shifted. So if you evaluate it at 12, we get the 12th apple, right? So since we have a polynomial, we can evaluate it at 1 million, or whatever this is, 1 million, right? And since we have a red apple in this original sequence, if we evaluate that polynomial at 12 million, we should get red or a bad value, right? And if we evaluate it at 1000, yeah, we should also get like a bad value. So,
like the original apple, that is what we are going to use to get our polynomial, right?
yes, that's what we're going to interpolate to get the polynomial.
So then you can now use it to get this other value.
Yes. So the major thing there is that after we have interpolated and gotten this f polynomial, whatsoever it is, whatsoever thing it is, if we evaluate that polynomial at 1, we are going to get this apple. If we evaluate it at 2, we get the next apple. If we evaluate it at 3, we get the next apple. If we evaluate it at 4, we get this apple. If we evaluate it at 5, we get the next apple. So if you evaluate it at like 1 to 15, you should be able to get the original set of apples. Does that make sense?
Then if we evaluate it at 16, we start getting
The extended, the blown up values.
So meaning that at the point at F16, we can know the content of the basket, whether it was red or green.
At F16.
Yes, at F16, if all the apples before F16 were green, F16, if the first 15 were green, 16 will definitely be green. But if any of the apples between 1 and 15 is red, then 16 will definitely be red.
Yeah, that's if we now want to check all of them again, right? That is after you've gotten the function. If you want to check the initial basket, you now need to do it one by one, right? That's like evaluating at 1 up to 15. And since you knew the initial number of apples that were in the basket, when you get to 15, like if you evaluate it at 1, 2, 3, 4, 5, and you're checking it, when you get to 15, you know that, okay, you have checked all the original ones.
So, but it's not like the original ones will be arranged in that sequence.
It will be arranged.
Because if it is arranged in that sequence, then that means that from the 16th upward will be the blown up values.
Yeah, it will be arranged in the sequence. It will be arranged.
So, this polynomial, is it the error function or the used for evaluating the computation that's actually?
No, this polynomial, we can see it as a polynomial that encodes the computation, because it's the values, it's the result that was gotten that we used to get the polynomial, right?
Yeah.
By interpolating, right? So we can see it as a polynomial that encodes the computation.
So what that makes it error amplification polynomial? What makes it what you just said now and transposes it to being the error amplification polynomial?
It serves those two purposes because you can evaluate a polynomial at any point.
Sorry, if I'm getting you right, we use it to evaluate at any point. That's it. Then secondly, you can now use it to check if anything was against or for any error to blow up for communication or something like that.
Yeah, by evaluating at any point and checking that point. So after evaluating at, let's say you evaluate at 5. After evaluating at 5, you get a green. You now check the original sequence. You get if it's actually green.
Why is F12 red?
The number shifted. The number shifted. So this top is actually meant to be here.
My question is, if you get a polynomial, 1 is green, 4 is red, and 12 is red, right? Is it automatic or there's a way we get a polynomial back? Anything after 15
In as much as we interpolated the polynomial with these initial values, the polynomial automatically encodes that data. I don't know if people went through the
I went through, that's what I'm asking.
you went through the polynomial block as we sent on the
So if you, I know substitute this with an encoded form of the polynomial, right? My question is, how sure are we that anything after 16
that's mathematics. Mathematics constant to do that verification. Are we comfortable up to this point? Like the whole polynomial for error amplification, does it make sense? Makes sense, right? Okay, so basically with this, we can make a computation asymmetric that allows the prover to do more work and the verifier can do very little work. Because the prover is doing the original this thing. The prover is doing the original execution and then doing more work to generate a proof. So the prover does the work of executing the program. And after executing the program, the prover does some extra work to generate a proof so that the verifier will do lesser work of just verifying by checking out maybe just 1 point or multiple points, depending on the verifier's, what the verifier wants to, like the percentage certainty the verifier wants to get. Does everything make sense up to this point? It may not make sense totally per se, but are we all together? Okay, so do we have any questions? Any questions? Okay, so if no question, I think we can take a little break and then we'll come back for the other parts. Okay. Okay, so we have this graph. How can we find the total number of triangles in this graph? That's the question of this part. So each edge or each arrow shows a connection between people. You can think of this as a network, right? And each arrow shows the connection between people. Sorry, this arrow is meant to be like bi-directional. The arrows. So if there's an edge, which is like a line between two people, it means those people know themselves, right? So that's why I said it's meant to be bi-directional, because like A knows B, and B knows A. Yeah, but this graph is showing something different. Based on the arrow, it's just showing like that A knows B, but B doesn't know A. So just bear with me on that. But we understand. Okay. So an edge shows that two people know themselves. And when we have a triangle, it's when we have three people that know themselves. So can somebody tell me one triangle in this graph? One triangle in the graph.
Yes, no, only one.
CAB. EFG.
ABC.
Yeah, ABC.
CBA.
Eh?
ACBA.
That one is like permutations of ABC. So we have the ABC and all its permutations, right?
We have G, F, and all these permutations.
G,
We have EFG and all these permutations.
EFG
Yeah.
and all its permutations, right?
FG,
FGH and all its permutations. Okay. Any other one? Just three. And their permutations. Okay. So I try to find the total number of triangles in this network. First of all, let's think of how we can make the problem programmable. Say we want to maybe write an algorithm for this. Right. So there are different ways of representing a graph. Right. So can represent it as an adjacency matrix. You can, like, there are still other ways that I can't come to my mind right now. But there are like different ways of representing a graph, and like the adjacency matrix is kind of one of them. So where a cell represents the connection between two people in that network. Okay. So let's look at this. We have like A, B, C, D, E, F, G, H, right? Which is like everybody in the network against everybody in the network. So this is like a matrix, right? You can think of it as the adjacency matrix. And you can see here A and B, right? Where A and B intersect, we have a 1 in it, meaning that there is an edge between person A and person B, right? So if we check, we can see this person A and person B, there's an edge, right? So that's another thing. Since there's an edge between person A and person B, that means we should have a 1 where A and B intersect, and also where B and A intersect, right? That's here, B and A. Right, so we have a 1 here and here to represent that edge between A and B. But if it was maybe a one directional, maybe A knows B but B does not know A, then we're just going to have it 1 here, right? Here will be blank. Okay, so since here we are dealing with a bidirectional graph, right, where A, if A knows B, then B knows A, like based on this edge.
Well, I thought the arrow just pointing in one direction.
Yeah, that's what I said. That's a mistake on my part.
It's supposed to be like.
Yeah, it's meant to be like there's meant to be an arrow. Yeah. All I'm trying.
Arrows here are like that.
Yes, all the arrows in this picture are meant to be like that, bidirectional. So, but if it was just like maybe a one directional, like as the arrow is showing, would have had just one here and not the other way around because B does not necessarily know A. Hope it makes sense.
Yes.
Yeah, so basically if we verify this matrix, okay, let's pick one at random. Let's go with this, right? GF, right? GF, right? So there's our edge between them. So basically we can represent this graph as this matrix. Okay, so now we have this matrix, right? Or we have this matrix, and the size of this matrix is huge. In the sense that if we want to add a new person to this network, we'll need to add one row and one column, right? Increasing the size of basically the size of this matrix. This should be n square, right? Yeah, n square, where n is the number of people in the network. Makes sense, right? Okay. So is it possible to reduce the size of the matrix? Probably make it just one line of text. How?
I'll explain how, but I don't know
Does anybody want to try?
One line of text.
Yeah. Probably just make it one line or just reduce instead of us always having to deal with instead of us always having to deal with that n square size matrix. Maybe just reducing the size somehow.
We got points like for every B, like you have 2 points. Or the E to E is since we know that E to E is just
Okay, pick one of it, right? Okay, yeah. Any other person?
It's more like a resultant. If you're looking at a right angle triangle, for instance, and you know the hypotenuse is kind of like the result of the adjacent angle. So I think since this is a matrix system, there's a way you can actually get a one result or get calculation to just give you one single value that represents the whole matrix.
So are we reducing the size or is the representation?
Let me call it the representation.
reduce the size of the matrix. The previous matrix that you're showing us just now.
Yeah, like is there another way we can represent it that won't require us to actually keep that n square space?
I'll go back to the diagram. This one.
Yeah.
Why don't we bring it together now? Fill up the remaining spaces. If we bring it together, why don't we solve it or something?
But you still want it to reflect the network, right? You don't want to make any adjustments to this that will make it to lose information with respect to the network, right?
It's something like a matrix equation.
Okay.
Like determinants also.
Okay.
Okay. I'll say the matrix equation is kind of, like you can write a program to represent this matrix, right? But that will require n squared space, as we have seen, right? It will require n squared space. So, okay, let's just go ahead and see. How about we present all this information on a curve? It's possible. So we present this on a curve. Wow. That is okay. So let's just go in. So we can represent all this information on a curve, right? But is that even possible? Is that even possible? Like, it's possible. It's actually possible. So given a set of points, we can generate a curve that passes through those points. Do we agree?
Yes.
Say we have a set of points. No matter how useless that curve is, we can actually draw a curve that passes through all of them. No matter how weird it looks. Okay. So given two set of points, or given the set of points 0, 2, 1, 5, 2, 9, 3, 15, find a curve that passes through them.
This point now.
No, this does not. No, not yet.
This point now, is it related to that matrix, or is it just like an abstract?
No, this is an abstract. Yeah, it's not related to the matrix for now. Yeah. So, in secondary school that year, when you want to draw a graph, like a normal mathematical graph, they will give you the x and the y value to plot the graph, right? So, which of this is the x value, which is the y? I know it's kind of like a basic question. The one on the left is the x, right? The one on the right is the y. We can see here like x, the x-axis is the horizontal axis. So we have x0, x1, x2, x3, right? And for x0, the value on the y-axis is 2. For x1, the value on the y-axis is 5. For x2, the value is 9. So if we plot this on a Cartesian graph, we'll be able to draw a curve that passes through these points. Do we all agree? Makes sense, right? Okay, so to draw a curve on a graph, we need an x and a y coordinate. The pair of points is usually presented as x, y, and basically what we've just said. So, literally speaking, what this means is that when x is 0, y is 2, right? When x is 1, y is 5. Like that. So, can this information be of any help to us with respect to our problem? Like from what we've talked about now, like it can, right? And how can we know, like in this case we're using like A, B, C, D, E, F, G, H, right, as the nodes. So how can we like represent this nodes or these people in the network in a way that we can represent it on a graph. Say if we want to now plot the graph, right? So to do that, we need to give each of these variables or each of these letters a label, right? Which brings us to this point. So
I have a question.
okay.
Last line. So you said we're going to use those points to try and plot the graph. So the purpose of plotting the graph is to get the equation of the problem.
Yes, to get the equation of the curve. So it's basically to enable us encode all those information in a curve or a polynomial, right? Polynomial is coming up again, right?
When you showed on that, you said something about trying to relate the sides, right?
Yeah.
And the side is like n times, which you can say is a polynomial, right? How do you see that?
N square in that case is talking about the cost, the space cost for representing the network. Does it make sense? Like when I say space cost here, do we understand what I mean by space cost? Because each of those cells will occupy, like, let's say if we're representing it as an array of arrays, say programmatically now, if we want to represent this matrix, we represent it as an array of arrays, right? Where each value in the array is the value there. I don't know if it's making sense. Okay, so we give them a label, right? So for A, we label it 0, 0, 0. For B, we label it, sorry Dave, I don't know, maybe it's because of what I'm using to visualize, like it shifted stuff. So for A, we label it 0, 0, 0. For B, 0, 0, 1. For C, 0, 1, 0. D, 0, 1, 1. And so on, right? Do these numbers remind us of anything? Binary, right? Okay. Okay, so we give each of those like each of those nodes a label, and with this, representing our matrix as a set of points. Now, this is what we can do. We can do something like this, right? So 0, 0, 0, 0, 0, 0 will be the first cell, which is 0, 0, 0, 0, 0, 0, right? Which is this cell. Does it make sense?
I have a question. So, why did we choose to represent it in like we choose to use binary, like?
Okay, we can decide to use any other, like we can decide to use, say, 1, 2, 3, 4, 5, 6, 7, 8.
Or even
Is there a way to use AA, use A, B, C, D, E? Is there a way to do it like that?
So do it that way.
Yeah, to use A, B, C.
No, why we are going this route is because we want to generate a polynomial, right? We want to generate a polynomial. That is the essence of us going this route. We are looking for the easiest way or the best way to enable us to represent that information as a polynomial, so that we can represent the entire matrix as a polynomial in its coefficient form.
Okay, that means the reason why we are using binary is to easily represent our value so that we can like
Yeah, so that we can get the polynomial.
okay, because I don't know, I'm trying to like think of if we are using something else other than this, how
it's going
easy
to
it would
be.
to like relate it back and all of that.
So that means you could have used something like x1, x2, like normal variables, and it doesn't affect anything.
Yeah, it doesn't affect. But the thing now is, when you're using the x1, x2, you're now abstracting, right? Abstracting in the sense that if, or let's,
What X is.
yeah, or if we want to get like maybe for the value in this cell, we will need particular values for D. Like, how can we represent D, the person D, as that x1, x2, x3?
And
Well,
that's like x4 or x3, depending on.
okay, but let's just like, well, let's just go a little bit further. Then we're going to still come back. Like, if we go a little bit further to see if like things get a little bit clearer, then we're still going to come back. Oh, that makes sense. Okay, so
Sorry, sir. So it's because of the that one that represents in the square brackets. That's why we're using this binary. Yeah. So if it was a different say maybe hexa, so maybe it would have been a bit different. Just to be able to represent this.
yes. Sorry, somebody had another question. Okay.
So I'm looking at this thing, it reminds me of when we are doing K-map. You know K-map, right? Canon map.
Yeah.
Now we are applying and use it to like stationary. So like
it will, right? Yeah, you can still use it. Maybe a key to a tuple, right? You can still use that way to represent the information.
apply for
Yeah, you now need to maybe work on a proving system that can work with it. You get?
this thing is just precisely like how K-map works. That's
Yes.
why I use it. I also use it.
Yes. Okay, so but does everybody like this 000,000 equal to 0? Does it make sense? Like, why is 0? So if we have something like this picture is messed up, but if I have something like 010, 001, it's going to be equal to 1, right? So this 010, let's say that's C, and 001, so that's this, should be equal to 1. It makes sense why it's equal to 1, right? Don't mind the shifting. Yeah. So this tuple makes sense, does it? So we just removed the comma, right? And we took this as x and this as y.
Based on the previous thing that we had, like everything got to one.
Yes. Based on this, where that was here, right? This x and y, right? Okay. So where x is this and y is 0. So it makes sense up to this point.
Sorry, is it X that is the 6 0? I was thinking like the X is the first 3, the Y is the last 3, then zero was like the result of like the meeting point of them what?
No, x is all of them. You know, like when you're plotting your graph, is f of x equal to y,
Yeah.
right? So x is what you're passing into the function, is the input
Oh,
to
what
the
you're
function.
passing into. So that means
Yeah.
x itself is like has like 2 points.
So yes, has like 2 points. So you can think of it like x. You can now, if you want, you can now break it down like x1, x2, x3, x4, x5, x6, right? As inputs to the function. Then y is the output.
Is the output.
Makes sense?
So, I think I see the reason why you said that mapping is like both sides, because you're saying 0, 0, 0, 0, 0, 0, 0, 0, 0, comma 0, 0, 0. Because how do you know the one which is
That comes first.
exactly?
Yeah. True. Maybe it makes sense. But if it doesn't, ask question. Makes sense up to this point, right? Okay, so now let's now break it. See, this might have been a wrong way to represent it, but like this x here means the first, yeah, the person on the left, right? This y here is the person on the right. You know, we're drawing a line between those people. Then z here now represents, yes, is there an edge between them? Makes sense. Okay. So if you want to do this for other points, so for 0, 0, 0, comma 0, 0, 0, which is like a comma a, right?
Or A, comma A prime, something like that.
This will be like a comma a, because it's still like 0, 0, 0 is
Just A
still,
on this and then A on this.
yes, a, yes, thank you. So that,
So the thing now is, there's still no point in using this binary, right? You just use the representation of A here and maybe A prime here. It will still be equal to 0 instead of 0, 0, 0, 0, 0, 0. I think 0, 0, 0, 0, 0, 0 is just like a naming convention to maybe something.
no, it's not a naming convention, because the 0, 0, 0 is telling us person A specifically.
You can still represent that as A now.
I think A is A everywhere now. A is
Yeah.
the same
But the
everywhere.
A
So
is
putting
still-
the prime on it is like giving it different identity.
Yeah, a different person. Well, let's just continue. So we're still going to abstract. We're still going to abstract this, because this is like this 0, 0, 0, comma 0, 0, 0 is talking about like A particularly. This is talking about A and B. This is talking about A and C. Right? So that's why we now represent it like as point values. We can remember this this array, right? Where we have the point and the value, right? So if we come back here, so we can see like this is a point, this is its value, this is a point, this is its value, right? But inside this point, it's still broken down into, yeah, the two people that we are checking the connection. So for all those points, we now generate like a set of, well, like for all the points in the matrix, for all the points in this matrix, like this one, this one, this one, this one, this one, up to the last, we now generate an array of points and their values. of which this array of points and values will be n squared. I don't know if it makes sense, because each point or each cell can be represented as one of these, right? Each cell in this matrix can be represented as one of those points and values. It makes sense, right? So we are going to have n square of point and values, like n square point and values. Does it make sense?
Yeah.
So that is just us now representing this matrix as a set of points, which still uses n square space, right? It's as if the n square space like through everybody. Eh? You know clear. But when I say n square space, do you understand what I mean by n square space?
Sorry. Because of the fact that two labels, label on horizontal and vertical, they are same.
Yeah, they are the same.
So that's why we have n square.
Yeah, if they were not the same, it's m times n. Yes. If it was not a square matrix, it would have been m times n, where m is the number of rows and n is the number of columns, right? So to get the total number of cells in this matrix is m, which is the number of rows times the number of columns. But if the both of them are the same, that is n times n, we have n squared. Yeah, space, because yes, this first guy takes up one unit of space. The second guy takes up 1 unit of space too. Yeah, space complexity. So that is the space complexity of this matrix, like, because basically adjacency matrix, or this way of representing it, like this adjacency matrix has a n square space complexity. I think there are still other ways to represent a graph that takes lesser space, like what he said, because it's like a hash map or something, right? Have like a lower space complexity.
So this is like a 2D array.
Yeah, this is a 2D array. Does it make sense up to this point?
Yes.
Okay. So does it make sense why we have like n square values in this array?
Yeah.
Or let me not say n square, m times n values in this array.
Yeah.
Does it make sense?
Yeah.
Why?
That makes sense when you explain it.
Like, does it make sense why we have n square tuples in this array?
Yes. Because each entity here is composed of 2 values.
Okay.
Every entity has 2 values, and then we have n of those entities. That will be n square space.
Okay, yeah. You can think of it that way too. So, like, breaking it down to the list, why we have n square values here is because we have n square cells in the matrix. Right? Please, if it doesn't make sense, if you get lost at any point, please ask. Like this one doesn't have anything to do with ZQ. Like all these ones are just doing is just to, would I even say maths? I would say it's just maybe system or software engineering, right? Just representing a problem programmatically. That's just what we're doing like right now. We're not even talking about ZK yet. Yet.
Even the red and green light,
We have not even reached that point. We have not reached that point.
See what I'm trying to say, right? That if you I think if you represented this thing as maybe AXAY 0, AX BXBY 1, this thing it might be easier
Yeah,
to
it's what I
understand.
mean.
You know, instead of all these 0, 0, 0, 0, 0, 0, 0,
Yeah, I thought going this route, will be. So, but that's why we now came down here, right? So yes, to now specify where we have A, B, C, D, E, F, right, equal to Y, right?
I think the reason why you went through this route was because we were trying to break it down into like A, B, C, D, E, F.
Yeah, so that people will understand.
So if you did A1X, O1X, I know you make it more mathematical, but then that's A, B, C, D, E, F.
Okay, so this is like a polynomial, right? Because a polynomial, now we are abstracting these values, right? Using A, B, C, D, E, F as variables, right? So if we want to now check for, say, A and A, that's why we now put concrete values. We evaluate this polynomial at the label for A is 0, 0, 0. So we have 0, 0, 0. And the label for A is 0, 0, 0. So we complete it 0, 0, 0. Right? And then we evaluate the polynomial P at all zeros, and we should get 0. Does it make sense? Okay. So we have a polynomial now. With this polynomial, we have abstracted the concrete values for everybody in. We have represented these points on a curve, which is represented as the polynomial, right? Because if we want to plot this polynomial, we just need to evaluate that polynomial at this point and plot the value of y, where we have f of x equal to y.
Can we see the plots and the graph? The next slide.
I don't know if we have that plot in here. I don't know if we have that plot in here. Yeah. But I don't know if like we are all comfortable up to this point of.
I didn't get to that part for that
Okay, the P part. This P part, in order to get this polynomial, we need to talk about polynomial interpolation. So for now, just think of polynomial interpolation as a black box. But just know that the way we can get the polynomial P from the point value representation, which is this is the point, this is the value, this is the point, this is the value, right? And we have a set of point and values, but then we want to generate a polynomial that passes through all these points. And how we can get that polynomial in the coefficient form is by interpolating these values. So for now, just look at it as P of x equal to y. Right? Just look at it as P of x equal to y. Just same thing with this. So we want to get a polynomial such that if we evaluate it at 0, we get 2. If we evaluate it at 1, we get 5. If we evaluate it at 2, we get 9. Right? Same thing with this case. we want to get a polynomial that if we evaluate it at, this is our value of x, this numbers of zeros is our value of x. So if we evaluate it as this value of x, we get 0. If we evaluate it at this point, we get 1. If we evaluate it at this point, we get 1.
So each of the 6 digits are paired to like A, B, C, D.
Yes, it's paired to A, B, C, D, E, F. Does it make sense?
The way me I'm seeing it, it's just like if somebody understand complex number, it's just like that. Real, imaginary, imaginary, anything. That's all.
Yeah, you can also think of it that way. So the thing is that the same thing we are saying, like everybody have their different way of digesting information, right? And it will be based on your own approach to understanding. It will be easier for you to remember if you use your own approach, right, to understanding. But the main thing is being able to understand it in a way that you understand it well enough to see it in different places. Because some things that you think are not related may actually be related if you understand it well enough. It depends on how you understand some things that you'll be able to draw the connection between things that doesn't seem to relate. And drawing connections like helps to retain. And if you're able to draw connection between things, it's easier for you to remember those things. Like remembering one of the node in that graph of knowledge can lead you back to the main information. I don't know if it makes sense. Okay, so for this example, basically our polynomial has 6 variables, unlike the p of x equal to y. This is p of a, b, c, d, e, f equal to y. So when we look at polynomials, we are going to look at univariate polynomials and multivariate polynomials. Right. For now, we can just think of it abstractly. But when we have a situation where we have like p of x equal to y, that's a univariate polynomial, meaning we have just one variable, which is x.
Sorry, why we use ABCDEF? Why not ABCDEFG? Can we extend the number of variables?
No, we can't add g here because 3 of this represents the person on the left, and this other 3 represents the person on the right. Does it make sense?
I don't get actually.
When we talked about adding labels, so A, B, C represents this, right? D, E, F represents this. And you can remember that each cell here shows that there's a connection between the person on the left, which is the person on the row, and the person on the right, which is the person on the column. It makes sense, right? Yeah. Does it make sense for everybody? Does it make sense for everybody?
Yes.
Is it getting boring? Eh? If it gets too boring, if it's getting boring, you can stand up and shake our body. Okay. So we have a polynomial that has 6 variables, which is p, right? And I said we are going to be looking at univariate and multivariate polynomials when we talk about polynomials. So So univariate polynomial, you can think of it as p of x equal to y. Right? X there is just one variable, p of x. But in this case, we have p of a, b, c, d, e, f. That's 6 variables. So it's multivariate, multiple variables. But we're still going to talk of like univariate and multivariate polynomials. So if we interpolate this point, we get a multivariate polynomial. Right? I don't want to go into the multilinear side of things, but one reason why we went this route was because we wanted that multilinear, we wanted the polynomial to be a multilinear polynomial. That's why we decided to go with the binary representation. But we are going to still talk about this when we start talking about like Boolean hypercubes and or like when we get to like polynomial interpolation. I don't want us to confuse ourselves with it at this point. So it's a step-by-step thing. Okay, so the process of generating the polynomials is not covered in this talk. To find out more about it, read up polynomial interpolation. Our people are already in the group, right? Okay, so this is what we're driving at. So the evaluations of the polynomial p of x. So if you evaluate it at a equal to 0, b equal to 0, blah blah, you get 0. If you evaluate it at a, b, c equal to 1, 1, 1, d, e, f equal to 1, 0, 0, you get 0, right? So we can represent that entire matrix as this polynomial. Do we agree? Because if we evaluate this polynomial at any of the points within the matrix, we are going to get the value at that cell. So with that, basically we've been able to compress that matrix into this polynomial, p.
Sorry, I have a question.
Yeah, okay.
With the current representation, say I want to look for polynomial at D and F. We can easily add people to this and do a computation 0, 0, 0, 1, 0, 0, comma C. But with the compressed calculated part, P, I guess he was asking that question, but I didn't get P, A, B, C, D, E, F. So what I was doing before was I was representing each of these the alphabets. But that's not okay. Because justice. You know what I mean?
No, I didn't understand.
Okay, so we have to do everyone.
Yeah.
Before, the first guy represents
This first one.
yes.
Yeah. So the B represents this guy. C represents this guy. D, E, F.
Yeah.
Okay.
Well, with what we have already, we have more than that. We have GH.
No, we don't have GH. Huh? Okay. Of A. Yeah, we've gone past that initial A, B, C, D. Wait, okay, I think I get your question. Like this A, B, C, D, E, F, G, H, we have gone past it. Like, forget about this A, B, C, D, E, F, G, H now. Anywhere you see 0, 0, 0, it means we are talking about this person A. Right? If you see 0, 0, 1, we're talking about person B. Right? So if you see 0, 1, 0, we're talking about person C. So 1, 1, 1 should be H. So anywhere you see 1, 1, 1, know that we're talking about person H. So, okay, based on that now, can you answer this question? who are we talking about? Like, which nodes are we talking about in based on this?
H and B.
H and
H and C.
H and C, exactly. So what we're trying to say here is that there is no connection between node H and node C, right? Can we verify? Is there node H and C is empty, right? Does it make sense now?
Yes.
Please, if you get lost, always draw us back. Ask questions.
Sorry, you made mention of, I don't know, you made mention of multilinear polynomial. And then you know, like what you initially said was multivariate, right? Like, what is multilinear?
We are going to, I don't want to go into it so that we don't confuse ourselves for now, but we are still going to go into it when we start polynomials. Yeah. But multilinear is just a variation of multivariate polynomials. But we are going to talk about it. For now, don't disturb yourself about it. Okay, so is this clear? This is clear, right? And like, do we now agree that the polynomial P represents our matrix completely? We agree, right? Can we remember the error amplification property of polynomial?
Yes.
We can, right? So what does that mean?
Means if you pass in values that are not within the range that we define as the key limit.
We still get a value of y,
Yeah.
right? So it means we can as well take a as 50, right? This a here, we can use 50. We can use 10, like b 10. We can use c 5. And evaluate this polynomial. We're still going to get a value, right? Does it make sense? But if we want to get the initial matrix, we need to pass in all possible combinations of zeros and ones up to 1 1 1 1 1 1, which will give us the beginning, like the first set of values. I don't know if it makes sense. The original sequence.
Yeah, don't get coming.
Okay. Like, but you understand it when I say that we can pass in like 50 for A and 20 for B. Like, we can pass in those values to evaluate this polynomial and still get a value for y because it's a polynomial. We're just evaluating the polynomial at that point. Does that make sense? So I'm now trying to say that if we want to get back this matrix, what we need to do is to evaluate that polynomial at all the values that make up this matrix, right? To get this this one, we evaluate it as 0 0 0 0 0 0. To get this next one, 0 0 0 0 0 1. To get this next one, 0 0 0 0 1 0. To get this one, 0 0 0 0 1 1. To get this next one, 0 0 0 1 0 0. Do you see any sequence in the counting? We are just counting like 1 to whatsoever this is in binary. When we get to the end of the row, we have 0 0 0 1 1 1. We move to the next row, 0 0 1 0 0 0. which is the next number in the sequence of counting, if you're counting in binary, right? And by the time we get to this, we'll find out that we must have counted all the possible combinations of binary numbers up to 111111. So 111111 is, what exactly is it again? Is that my calculator? Okay, so we're actually counting to 63, right? So yeah, so what they're trying to say is that, yeah, A to H is 8, right? A, B, C, D, E, F, G, H. That's 8, right? And 8 square is 64, right? So counting from 0 to 64 in binary is basically going from 0000000 to 111111. Does that make sense? Makes sense, right? Okay. Please, if you're lost, ask questions. That is why we're here. This makes sense, right? Very well. Okay, so with that we can represent the matrix as this polynomial. I don't know what the polynomial was, whatsoever it is, whatever thing it is. After we do that interpolation using the point value representation, using these values, once we do that interpolation, that polynomial we get actually represents this matrix. Okay, so now we've been able to reduce the matrix to a polynomial, right? So now let's think of how we can use the polynomial to find out if there's a triangle between three people. Can anybody yeah, so this polynomial, if you evaluate this polynomial, is just to check if there is a connection between two people, right? So now I want to check if there is a connection between three people. No.
Please, can you go back to the previous slide? Go back again.
But it's something like, like 1, 2, 3. Maybe like something like 1, 2, 3. Not because something like 1, 2, 3.
Okay, it's close actually. Like that's the way I wanted to explain it, that it may not be easy to understand at first, but if you think of it that way, you'll be able to like generalize the intuition. But I think let me not go that route so that I don't. Okay. Okay, so So we have gotten a polynomial now that can check the connection between two people, right?
Yeah.
But we want to check the connection between three people.
So if we check between A, B, and we check between B, C, then
Also, if you check between
A
A,
and
C,
C, because
yeah.
find the chance to see. So if A and C, and then A, B, and B, C are the same way, I think that might work.
Yeah.
So how do you represent that? How do you represent it as a polynomial? Is that how do you
Not really representing it as a polynomial, but coming up with an expression. Thank you.
you can give discrete values, right? And then
Yes.
check if there's a connection between them.
Yeah. So, okay, let me just shoot. So we know that when we evaluate the polynomial at valid points within the matrix, we get a 1 or a 0. If there's a valid connection, we get a 1. If there's an invalid connection, we get a 0. And we know that a 0 times anything is 0. Right? Is this ringing any bell now? So, okay. Yeah. Let's see. Yeah. Must give us a 1. Yes. So, we know if we have ABC, right? So, if we have ABC, right, in order to, we have a polynomial that can check if there's a connection between two people. So we can check A and B. If we check A and B and we get a 1, okay. We can check B and C if there's a connection. And we can also check A and C. If we check the three of them and we get a 1, that means there is a triangle, right? But if one gives a 0, that means there is no triangle. So if we multiply the three of them, like P evaluated at A, B times P evaluated at B, C times P evaluated at A, C. It should give us a 1 if there is a triangle and a 0 if there is no triangle. Makes sense, right? So yeah, so that's it. Yeah. So we're passing P, X, Y, Z, right? A is the polynomial that checks the connection between two people. In this case, right? So we check X times X and Y, is there a connection between them? Times X times Z, is there a connection between them? Times A times Y times Z, is there a connection between them? So if any of these values is a 0, this polynomial P will return a 0, which means that there is no triangle. Okay. So that's just basically what you're saying here. So if we want to check that there's a triangle between F, G, and H, we're passing P of F. This is the label for F, 101, right? And the label for G, 110, and the label for H, 111. So based on the way we define the P polynomial, for A we're passing X and Y, right? And here we're passing X and Z and Y and Z, right? So if we evaluate these functions, we get 111, which gives us 1, meaning that there's a triangle in this. But if there was no triangle between any of them, one of these will be 0, which will make this entire equation to be 0. Yeah, the product. So now can we find all the triangles in the network? Now we've been able to come up with a polynomial that checks if there is a triangle between three people, right? Which is our P polynomial, which extends the A polynomial, which checks the A polynomial checks if there is a connection between two people. So we use the A polynomial to build the P polynomial, which checks if there is a triangle, right? Now we want to use that P polynomial to check if there is to count how many triangles we have in the network. Okay, so we can find all the triangles in the network by checking every possible combination of three people in the network and summing the results. So every possible combination of three people in the network, we check if there's a triangle between them. If there's a triangle between them, it will return a 1, right? Then we now check another combination. If it returns a 1, we just keep accumulating the 1, right? By the time we check every possible combination of three people in the network, we should have the total number of triangles in the network. Does it make sense?
Yeah.
Makes sense, right? So although based on the permutation thing, yeah, so there'll still be some extra duplication that will need to be removed. There's a general formula for this, but we didn't factor it in the presentation. So this is a computationally intensive task because you're evaluating that P polynomial at all possible combinations of people in the network. So that P polynomial, let's say it's A, B, C, D, E, F, G, H, I, right? So you're basically going to evaluate, you're going to evaluate this polynomial at 2 to the power of 9 points. Does that make sense? Okay, when I say we are going to evaluate the polynomial at all possible combinations of three people in the network, does that make sense?
Yes.
Okay. So
I think if there's a way that we could represent it on that adjacency matrix, right? Where you can now see the 3 points that you're trying to represent that. Because that's a 2D array. You can represent it as a 2D array.
Visually, yeah, but we can't. Yeah. But yeah, the number of triangles. Huh? Yeah, all the possible three people. Yes. You say, and there are 8. 8 people. Okay, no, there are 8 people in the network. Okay, yeah, I think I know where you're going. Yes. To get the total number of, the total possible combinations, exactly. Is it 56? No, it's not. All possible combinations. Based on certain conditions. You get? Wait. Sorry, are we together?
Yeah.
So we're trying to get it would have been easier the way you said it, but you know, like we've tried to represent the problem programmatically, giving each person a label, right? So giving each person a label now, in order to get all possible combinations of three people in the network, we need, how do I put this, that okay, let's so here, if we want to start counting, okay, let's just use this way and see if it works. So we have P, right, which is the function that checks if there is a connection between three people in the network, right? And if we want to check every possible combination of people in the network, we are going to start from 0, 0, 0, 0, 0, 0, 0, 0, 0. But that's kind of like cyclic, because we are checking if A is connected to A and A. If A forms a triangle, A on its own, if A forms a triangle, right? Which is not possible, right? So the next thing will be like, or AAB, right? Then the next one will be AAC, AAD, AAE, AAF, AAG, AAH. Yeah. Not necessarily 0, 0, 0, but depending on the value we get. That is 6 possible combinations. Okay, for AA, right? For AA to be 8, right? No, for ABC, right? We'll be having that's 3. So that should be that'll be 3 to the well, let's just right. I'm trying to make us see why there will be 2 to the power of 9 combinations. Right. What's 2 to the power of 9? That's 5.2. 5.2 different combinations. It's just similar to why we have 2 to the power of 6 here. 1 or 2, 4. But 2 to the power of 6 should be 64, right? That's 64. 2 to the power of 6, and 111 is 64. I don't know if it makes sense. So 111 111, that's 63 plus the 0, plus 0, so that's like 64, right? So counting from, this is just for checking 2 people, right, which has like 6 variables. When we extend this formula and get P that checks for 3 people, that's 9 variables, right? And for basically trying to check all possible combinations, that is all zeros to all ones, right? And all ones basically is that's 2 to the, okay, let's just, yeah, 111, exactly, that's 255. Yeah, missing one more. Yeah, that's 5-1. Yeah, that's 2 raised to the power 9.
Just for 9
Yeah, 2 raised to the power 9 is 512. So it's basically more like we're counting from 0 to 512, but we are just representing the number as a binary number in order to check all possible combinations of all possible combination of 6, or sorry, all possible combination of 9 variables that can either be a 1 or a 0.
Is it not going to be like, because we're counting, what's it like, what, you have 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0. Okay, so like, if you have, so we have like, is it possible, 8, we have 8 on like, okay, we represented them as like 0, 0, 0, 0, 0 on this line, so if we have like 8 on this guy, and this, sorry, how many variables? We have 0 to, we have 9 on this side, and we have 9 on this side.
No, we are not representing. We have gone past that adjacency matrix.
Now I'm talking
That,
about representing the vector.
yeah, like that adjacency matrix. After we converted the matrix to the polynomial that we can use to check if there's a connection between 2 people, you can think of it that we are done with the matrix, right? So we now built on top that polynomial to get the polynomial that we can use to check if there is a triangle between 3 people in the network. That is where we now have this guy. That's why we now have this guy P, right? That builds on A, that checks if there's a connection between 2 people. But the thing now is that we are passing in 3 people to this function P, right? And then based on those 3 people we pass in, the function returns a 1 if there's a connection between them, right? But we now need to check all the possible combinations of 3 people in the network. We need to evaluate this function at all possible combinations of 3 people in the network. Does that make sense?
I think. So why do they have to do like 3 is 5?
It's because we have 9 variables. This is 3, yes, 3x is ABC, right? Y is DEF, and Z is GHI, which is 9 variables. So this P function takes 9 variables, right? And out of those 9 variables, it splits. Yeah, A takes 6, right? This other A takes 6, this other A takes 6. But what we are passing in to the function is actually 9 different values for the 9 variables. So it's internally that the function is now splitting it. Yeah. So we can just think of this function as like a black box that we pass in inputs, and then when it wants to evaluate, it does a splitting by itself internally. Right.
I don't know where the ninth variable.
You know, like each variable here is made up of three
3 bits.
yeah 3 bits. So X is made up of 3 bits, Y is made up of 3 bits, Z is made up of 3 bits. In total, that's 9 bits.
But are we overlooking I don't know if it's a fact, but we will never be the polynomial here will never be checking, for example, there will never be an AXX or AYY. So why are we considering all the possible combinations? Because there is no point at XX. Sorry, there is no H.
Yeah, but the point this equation will check it. Like if we pass in 0 0 0 0 0 0 0 0 0, what we are going to do is check it. X is 0 0 0, Y is 0 0 0, right? Which is like checking AA, which is what you're talking about.
Would we ever check that? Because there will never be
Yeah, there'll never be, but we are going to check it. When we check it, it will give a 0. So when we multiply through, it's going to give us a 0. And in the grand sum, it's not going to add, because you know where it's not going to be a triangle, and you know we are evaluating it at all possible combinations of x, y, and z, and we are summing the results to give us the total number of triangles in the network. So in that case, since we get a 0, when we add it to the grand sum, it's not going to change anything. But we're still checking it. I don't know if it makes sense. But if it doesn't, like, and I know like it's complex. Or if it doesn't make sense, just okay.
Yeah, so the question I want to ask for clarity, you know, there was something you said about 2 raised to the power of 6 and 2 raised to the power of 9.
Yeah.
So what are we doing with that? Like, I got lost what we are doing with the 2 raised to the power of 6 and the 2 raised to the power of 9.
Okay.
Then also, the 2 raised to the power of 6, assuming that, okay, the 2 is based on the fact that we are what makes up a particular individual is two
Binary.
two different you know, we have six bits, but they are separated into two.
Okay.
And so I'm checking that, okay, that 2 raised of the 6 bits. Then for the case where we are like evaluating if 3 persons are makes up a triangle, or if 3 persons are connected, we are now doing 2 raised of 9 in the sense that
You're expecting it to be 3 raised to the power of
no,
something.
I'm not expecting to be 3. Why I'm not expecting to be 3 is because we are not evaluating like 3 persons at once. We are evaluating 2 persons, then multiplying it to check if it gives us 1. But the evaluation, like the bits in the polynomial itself, is made up of 9 bits. So that's why it's 2 raised to 9. I don't know if maybe what I'm saying is adding up.
I think like you get it to an extent, but I think you're mixing things up with respect to like why we have that 2 there.
Yeah.
So why we have that 2 there is because we are dealing with binary, right? So each of those bits can either be a 0 or a 1 with respect to okay, let's just use this for example. This A here can either be a 0 or a 1. B can either be a 0 or a 1. C can either be a 0 or a 1. Right? Up to F. Right? So that's why we have that 2 there. Then to the power of is the number of variables. Yeah, which is like the number of bits. Because you can think of this A here as a bit, which can either be a 0 or a 1, right? Then so since we have six variables here, we can represent 2 raised to the power of 6 possible numbers with 6 bits. I don't know if it makes sense.
Yeah. So that means, okay, yeah, I get what you're saying.
So this function now is the function that checks if there's a connection between 2 people, right? So for the function that checks if there's a connection between 3 people, I think maybe I would have, like, we'll say need to expand this further. X will be expanding X to A, B, C. We'll be expanding Y to D, E, F. We'll be expanding Z to G, H, I. That's 9 bits, right? Where each bit can either be a 0 or a 1. So a 9-bit number can represent numbers up to, or 9 bits can represent numbers up to 2 to the power of 9. Right? And that 2 to the power of 9 shows the total, like all combination of numbers between 0 and 2 to the power of 9 can be represented with 9 bits.
But if you are going 2 to the power of 6, 2 to the power of 9, I don't not like compare possible combinations that like could integrate to them.
The 2 to the power of 6 is like all possible combinations for the connection between two points, 2 nodes.
Okay.
I think like maybe we're mixing up checking if 2 nodes are connected with checking if there is a triangle between three nodes.
So we just got the 2 to the power of 6 because each
No, that 2 to the power of 6 just like that was just something that came up in our discussion, right? But 2 to the power of 9 is the total, the possible combination of 3 people in the network, the total possible combination of 3 people in the network.
Okay, that's because we have each of them have 3 bits.
Yeah, because each of them has 3 bits. So for the first one we have 3, the second one we have 3, the third one we have 3. That's 9 bits, right? And that 9 bits, each of those 3 bits can either be, say, 0 to 111. It can go from 000 to 111, right? Each of those 3 bits. When we join them together, we can go from 000000000, which is all zeros on the 9 bits, to 111111111, which is like all ones on the 9 bits, right?
So the total number of variation or the total number of
possible
0000009 is all is now 2 to the power
it's
of
2
9.
to the power of 9, exactly.
And calculated and that's
Exactly. Yes, that is it. I don't know if it makes sense. That's why, like, it's more like counting. It's more like counting from 0. Like if you want to use like decimal, right? It's more like counting from 0 to 2 to the power of 9. I think 10. Is it 51? 511. 512, right? So it's more like counting from, like if you want to count in decimal, it's more like counting from 0 to 511, right? If you want to count in binary, it's more like counting from 000 in 9 places to 111 in 9 places. It's still, those two things are still the same thing. It's just that you're counting in a different
So
base.
it's 2 to the power of 6. 64.
64,
It's
yes.
64.
Yeah.
Oh, so that means there are like 512 boxes for
So to the power of 9.
talking about 9
Yes.
3 XYZ, like 3 dimension.
Yes.
Yeah.
It's, I still mean like I've lost a lot of people. But that doesn't make sense up to this point.
Yes.
So let's just talk about the problem statement again, right? I'm trying to count the total number of triangles in the network. And in order for us to count the total number of triangles in the network, we need to check every possible combination of 3 people in the network. So that statement, checking all possible combinations of 3 people in the network, that is what brought us to like what is the total number of possible combinations. That is what brought us to that 2 to the power of 9. Right? So that is just what it means, that there are 2 to the power of 9 possible combination of 3 people in the network because of how we represented it, right? Because like one person is represented as 3 bits, another person is represented as 3 bits, another person is represented as 3 bits. If one person was 4 bits and say the second person was 4 bits and the third person was 4 bits, that would mean that it will be 2 to the power of 12 possible combination of 3 people in the network. Oh, that makes sense. Oh, I'm not started talking about ZK, oh Lord. Okay. So that's like a lot of work to do. You may think, sorry, please, can you give me a minute? Okay, so does everybody agree that we have 2 to the power of 9 possible combination of 3 people in the network? Yes. Everybody agrees? Okay. So in this case, what is the problem statement? The problem statement is that we are trying to find the total number of triangles in the network, right? Which means we have about 2 to the power of 9 evaluations of this P polynomial to do. Does that make sense? 2 to the power of 9 evaluations of this P polynomial. But this P polynomial may be a very big polynomial, right? Maybe a polynomial of degree, let's say 1 million. It's possible. Okay, so evaluating that big polynomial 2 to the power of 9 times, 2 to the power of 9 may be small, maybe 512, may be small, but the polynomial may be big, right? So evaluating that polynomial 2 or 512 times may actually be a lot of work. You get? So the idea now is, us as a verifier, we don't want to do that work. We don't want to evaluate this P polynomial at 512 points, probably because the polynomial is a big polynomial. We want to just evaluate this polynomial at 1 point, right? want to evaluate the p polynomial at just 1 point, but then we'll be able to, like with 100% or close to 100% certainty, we'll be sure that the person we told to help us do the actual calculation did it correctly. Does it make sense? So in this case, we are the verifiers. We actually had the job of evaluating this p polynomial at 2 to the power of 9 points and adding the answers, right? In order to get the total number of triangles in the network. But that's a lot of work for us. We don't want to do that work. We want to delegate the work to somebody to evaluate this p polynomial at 2 to the power of 9 different points and give us an answer. And then based on the answer the person gives us, we either accept or reject the person's claim that what the person gave us was actually the evaluation and sum of that polynomial over 2 to the 9 different points. Does it make sense? Are you sure it makes sense? Okay. But if it doesn't, ask. Okay. So the problem statement is finding the number of triangles in the network, right? And from what we've seen, we've been able to generate a polynomial that checks the number to check if there's a triangle between 3 people, right? But we need to check all possible combinations of people in the network. You understand that? And you understand the fact that there are 2 to the power of 9 possible combinations of people in the network. But evaluating that polynomial at 2 to the 9 different points is a lot of work for us. We don't want to do that work. We want somebody to do that work, but we want to be able to verify that the person actually did the work correctly. Because we can tell the person to actually evaluate and to do the evaluation and the sum, but say the person can just lie to us, right, and tell us that the final answer is 12. There are 12 triangles in the network. Say maybe because we don't have the enough compute to actually do the main work. Yeah, thank you. So we want to be able to delegate that work to the person, but also verify that the person actually did the work without us doing the work. Does it make sense? Thank you. So can we see the concept of prover and the verifier in this scenario? Who is the prover and who is the verifier?
Prover is the one that did the work. The verifier is just assessing what's done. Verify what
Do we agree?
Okay, yeah, so like the provider is the one that's doing like the work, doing the computation, and then the verifier is also like assessing what the person did, who has done, like verifying what who has done.
Huh? The prover, yeah, the prover will get the prover. At a random point, just one random point. And you know that like the verifier can, like based on the fact that it's a polynomial, the verifier doesn't need to evaluate it as binary numbers, right? Like as I was saying initially, the verifier can decide to take A as 50, take B as 70, take C as 1 million, take D as something else, but then still be able to like verify that the probe actually did a good work. So the problem statement makes sense up to this point. Are we sure? All of us are nodding. Are we sure?
Yes.
Okay. Now, it's now we're talking of the subject protocol. All the things we've been doing, like nothing concerns subject. And now it's subject one starts.
Yeah.
By the time, this 151. It's 151. Or should we do some checks? No, we should also consider people that watch the video, right? Because some of them may not be able to sit for so long and be watching the videos. So I think it makes sense for us to take a break for today and continue with the subject protocol tomorrow. What do we think? But it will be accumulating now. Yeah, because tomorrow now we'll like release another one, right? And if they have not finished this one, it's be a problem.
Position choke.